All right, good morning. There's one seat in the front if anybody wants to take a seat, but this is taking motor control to the next level. We're going to cover basic like PID and feed forward for running motors on your robot. So I'm Andy Gosser. I'm from team 7028. I'm a mentor. I had two kids go through the program. Now one is in college, the other's graduated, working as a software engineer. FRC, I started in 2018 when 7028 started, and I do programming and control systems with the team. And I'm a volunteer CSA. I'll be at Granite City Regional this year and Great Northern, and I usually do an off season or two. And I am an SCSU graduate. Thought I'd throw that on there since we're at SCSU today. So the first thing we'll cover is bang bang motor control, and I have a video that we'll kind of watch in little segments, and then we'll talk about it. So we'll start with bang bang.
Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't.
All right, so bang bang control basically is if I'm on one side of my target, I run, at full speed to get to my target. If I'm on the other side, I run at full speed to get to the other side. It's really simple to do, and there's no tuning required, right? You're either above or below, or you're right on the target. But it's like trying to drive a car when you use a keyboard on a video game. Like, it's really hard, right? You kind of are tapping back and forth. And so this is kind of that example here. The target is here. They're really close to the target, but they're still running at the same speed that they would be over here. So that's a really simple approach to start, but you don't get a lot of control, and you'll probably end up, oscillating around the target a lot. So we don't usually do that very much. Maybe for a flywheel that might be good enough, but usually we get more advanced into PID. So we'll start with P for in the PID control.
One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang-bang control, but it still doesn't work that well.
All right, so proportional control is like bang-bang in that if you're above the target, you run in the opposite direction. If you're below, you run the opposite. But now, as you start to approach the target, you give less correction. So that video calls it cross-track error. I usually just call it error because it's easier to figure out. But the correction is proportional to the error. So over here, we're really far from the line, so we have the largest correction. And when we get really close or right on it, we have very little correction. So the correction is proportional. This is the most common in control in FRC, is just to use P for proportional control, and you'll get pretty good gain, or pretty good performance like it showed, but there's still some opportunity to do a little bit better. So proportional control does require some tuning because you'll have your error value that you'll find, and then the P proportional value just gets multiplied by the error. So a lot of times people are like, well, what should I start with a number for my P value? And it all depends on your units. Is your error in centimeters? Is your error in rotations per minute? So it's going to be multiplied by the error to get your output. So it also depends on what kind of output mode you're using. If you're running your motor in voltage mode or say percentage output, the p-value will be different. But it's a very simple calculation to do. You figure out, what is my target going to be? What do I think my error is going to be? And what do I think my output should be when I have that error? And so kind of you can do a starting point. And if your p-value is too low, you'll be slow to reach the target, because when you get farther away, you're going to multiply by that p-value and your correction is not going to be steep enough and it will take a long time to get there. But if it's too high, you'll get to the target fast, but you won't slow down as you approach the target and you'll end up oscillating around the target. Or like it showed here, if you have a very high p, you could spin out of control where you actually never reach the target. That doesn't happen very often, but that sort of thing can happen. So the next gain in PID is derivative, and we sometimes use a little bit of that in FRC.
Proportional control returns better results than bang-bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering committee. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be zero. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now,
All right, so D is the derivative, and it's the rate of change of the error. So how fast are you moving toward or away from your target position? And then we multiply that by a gain to get the output that we want. That's just that video. So it helps us predict future behavior, right? Like how fast are we approaching that target so we can dampen the movement as we start to approach that target. So we could use a larger p-value to get to the target faster, but D would help us slow down as we approach. So that can give you a little bit better stability, and it's multiplied by the error to get the output. So the problem though, well, we'll get into that actually. If you get too much D, you'll be over dampened.
this rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel if it's moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to zero. This is called being critically damped.
So I like in that video how it explains the derivative gain as resistance to approaching the target. That makes a lot of sense in my head, right? P is trying to get you toward it. D is helping you dampen how fast you're getting there. So if you underdamp, you'll still overshoot and oscillate. Like if you have too high of a p-value, you get there too fast and you oscillate it. It doesn't do what it needs to do. But if it's overdamped, it's resisting moving toward the target fast. So it'll be really slow to reach the target. And then that critically damped is where you get it tuned just perfect, where you get to the target really fast. D helps pull it back so you don't reach it too fast and oscillate. And the last one is I in PID, and it's integral. For FRC, probably you won't use it. Usually, if you're starting to think you need I, you should think about other things. And we'll get into some other options for that. But here's what I, and we'll talk about that.
Despite the success so far, for complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there's a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks, which knocks its front end out of alignment, and therefore a zero steering command no longer keeps the vehicle driving straight. As you can see with the controller that has been described so far, the vehicle experiences a buildup of a lane oscillate, or steady state error. One way to address this problem is to add yet another term called an interval term. This third measurement sums up the cross-track error to give an indication if we are they're spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more time on one side of the trajectory. The integral term you propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable, because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front-end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other
So I helps in some of those scenarios with some unexpected outside forces like that, but it's difficult to tune. Like I said, you have 3 terms to tune now, so it's difficult to tune in the real world. And FRC matches are really dynamic what's happening. Like you saw when it changed the target, it had trouble getting there because the error is accumulated over a period of time, and now the target changed, so the error changes a great amount at once. So like within an FRC match, it isn't necessarily the right choice. And it amplifies any sensor noise. So sensor noise is like I'm actually spinning my wheel at exactly 5,000 RPMs, but my sensor is gonna fluctuate a little bit. It might say I'm going 4,725 and then 5,250. It amplifies that little bit of noise because I accumulates over time. So feed forward, we'll get into that next, but that's often a better solution for FRC. If you're tuning like a flywheel or something and you're starting to see that, oh, it's not quite reaching the target and you're tempted to use I, that's not exactly the right choice because it's more for like those unexpected things like the wind in the example or the alignment gets knocked out. So if you're in the shop tuning it in perfect conditions, you probably don't need I. Any questions at that point? PID is kind of our first topic, and then we'll get into feed forward. Have you guys heard of PID before, or is this all new? Yeah, a lot of yeses. That's good. Okay. All right, so we'll get into some demos then. On the WPI Lab documentation site, there's some really good demos for how to use PID. And I'll try to zoom out a little so we can see the whole thing, but hopefully not make it too small. Okay, so this is a turret example, and a turret is like something that turns. A lot of teams use them like to shoot balls. They'll have a turret that can pivot on their robot, and you're gonna say, I wanna turn it to 25 degrees, right? So you're gonna need to snap it over there. This is a example of that down below. We have this turret here, both its target position and then where it actually is. So right now it's set to 0 radians. In the unit circle, 2 pi radians is 1 rotation. So if we do like pi, we're trying to get over here and we have PID all at 0. So it doesn't move, right? The error is 3.14, multiplies that by P, and it gets 0, so there's no output. It doesn't move at all. So we could just say, well, what if we use 1? Well, now that's obviously too high. It's oscillating wildly out of control, right? So say, okay, let's try 0.5. We're getting closer now. And so it's probably a little bit lower because it's still oscillating quite a bit. Now we're getting pretty good. So we could try adding some D. That's too much D, right? It's like over damped, it's going kind of wild. Now we're starting to see that we're getting close. Maybe we want a little bit less P. Now we're getting pretty good. So we have 0.25 for P, 0.01 for D. And then we could try, let's say we pick a different positions and see how does it go to those positions too. And we're getting pretty good. It overshoots a little bit, so I'd probably want to tune that a little bit more. But for our example, that's great. And then down here, it gives us what did they think the optimal solution was. And they had 0.3 and 0.05. So let's see how theirs works. Yeah. So I would maybe argue stops a little bit too early. I would like my turret to be a little bit faster than that. But it kind of depends what dynamic you want. So right here, see, it gets dampened when it gets here and then goes real slow. But it does get right to the target and doesn't overshoot. Does that make sense how that works? Any questions on that? Yeah. Yeah, the question is, are you trying to get T, the amount of time, to the lowest number? That's probably true. It depends on your, what you want, yeah. Yeah, some overshoot might be better because you'll get there faster. So like that, the gains that I had got us there a little bit faster, but it did overshoot. So it kind of depends what dynamic are you looking for. Yep. If you want perfect precision, it may take more time. Yep. But that's what tuning the gains is all about. So there's a lot of tools in FRC depending on your control system. You'll want to hook it up and get a graph and kind of look at the time and see how it's doing. Don't just look at it and see how it's working. Try to get some actual data. Yep. Any other questions at this point? All right, so then, that's weird. Feed forward is the next topic. So PID is all about feedback. We look at how the system is performing in the past and then make correction for what we want, how we want it to behave in the future. So it's based on an observation and then we do a correction. So that's why it's feedback. Feed forward is we try to make a prediction. So we'll know that, like, obviously forward motor control makes the motor go in one direction, but we'll, so that's what feed forward is kind of about. You can model it in a lot of different ways, but we use pretty simple concepts in FRC to model it. And even really simple, especially when gravity is involved, really simple ways to do feed forward can help a system a lot. So KV is our first gain. It's the voltage per unit of velocity. So if you think of, like, let's say I have a motor that runs 6,000 RPMs, or I have an example right here. Motor that runs at 1,200 RPMs. When I give it 12 volts, I expect it to run at 1,200 RPMs. If I give it 6 volts, I probably expect it to run at about 600 RPMs, right? So that you can observe that behavior and tune your KV. And that can help you then get to the target faster because you know your velocity. Let's say I want to get to a velocity of 600. I know I probably need to apply 0.5 power. But if I'm starting from 0, I want to apply 100% power until I start to get close. So KV will help add to that and help you get to where you're going. So there's some great examples again on the WPI Live documentation. So this is a flywheel that's going to spin. And this is simulating a ball going through and shooting. So you first, like if you're going to shoot 2 balls, you're going to be thinking about how long does it take to spin up, because probably I have to drive over there, I have to aim, I need to spin up my wheel, and then I'm going to shoot. But I also need to think about how long does it take to recover, because I want to shoot a second ball, and I don't want to be sitting over there for a long time. So the set point here is 300 RPMs. And so let's just try 12, just to see what happens. And up here, this is graphing where it's actually going versus our target. And it just way overshot, right? We just ran it like 100%. So let's try something way smaller, 3. 3 is still very large, so let's try 0.25. Still very large. 0.025. There we go. So now it's taking a really long time. So when I'm tuning PID, I kind of like to double things until, so I did a factor of 10, which was too much. So, whoops, I lost my 0. Okay, we're still too high. So this will probably, nope, not quite get us to the target before it shoots a ball. So now we overshot, but we got pretty close, and then the recovery time is about the same. So let's see what they said. 0.0075 was what they liked. So that probably gets rid of that overshoot. Yep. So that gets us there. And a lot of times this is where people start with something like a flywheel, right? Is I've got a flywheel, I'm gonna need to shoot some balls. What if I just run the motor at 0.5? You'll run the motor, you'll know what speed you're gonna get to, but it'll take a long time to get there because it doesn't apply 100% power until it gets to it. It just immediately applies 0.75 power or 0.0075 power. So feed forward, we combine that then. So here's a combination of PID and feed forward. So we would start with our feed forward that we brought over from here, so 0.0075. And hopefully we'll see the same behavior. Yep. So then our goal is gonna be to get to the target faster and to recover faster. So let's just say we add 1 for P, it's probably gonna be too high. Yep, it's way too high. So 0.25. Now we get there pretty fast, but we overshoot a little bit. So I'd probably make it a little bit smaller. Try to get rid of a little bit of that overshoot. And then we could add some D to help with that overshoot. So now we get pretty close. There's a little bit of weird oscillation. So I would still probably tune this some more. But if you compare that to our graph over here, which didn't work right. Okay, here's 0.0075. Okay, so it takes a long time to get to the target, right? Now, once we use PID with feed forward, we get to that target real fast and we recover real fast. So I bet their tuning solution is a little bit more refined. Yeah, 0.1, so we ended up pretty close, and they used no D. Yeah, that snaps and no weird oscillation. So especially like that recovery really is faster. So we can cut that time down. Any questions about just KV feed forward and how it helps us out? All right. KG is our next term, and this one helps us a lot in mechanisms that have gravity affecting them. So an elevator would be just something that linearly moves up and down. So think like a forklift or something like that. There's output that's required to hold the elevator in a lot of cases because gravity is pulling it back down and there's probably nothing stopping it from going back down. And another gravity impacted mechanism that's very common in FRC is an arm. So think like some sort of a mechanism that pivots like this. An arm is more complicated because there's more gravity when it's out like this, and there's basically zero gravity affecting it when it's up like this. So an elevator has constant gravity all the time because it's just moving up and down. The arm has this pivot, so it's more complex. So let's look at what kg would be. Kg should be just the force that it takes to hold the mechanism is usually where you start. And so like for an elevator, that helps us a lot because otherwise, let's say I use 0.5 output and it makes my elevator move up this fast, 0.5 output is gonna make my elevator go down a lot faster because gravity is pulling it down on top of the output that I'm putting on it. So if you wanna get smooth output up and down, you have to add some output, right? Just enough to hold it up and then have your PID just do the movement with it being held. So this is if we were to just use feedback, just PID, we're gonna try to get to a set point that's up here, and now we have 0, so it just falls immediately because there's no output. So 0.1 is too small, 0.5 is too small, let's go 2. Okay, now we start to move up, but if I make my target something low, like 0.5, it has a hard time getting there. So their optimal solution here is to use 5 for P and 1 for D, but we'll see there's kind of some weird behavior there, right? And especially if you were to go somewhere like 0.1, it has a really hard time getting there because of gravity, where it gets there nice and smooth up at the top where there's very little gravity, but when there's gravity pulling it, it has a hard time getting there. So this one combines kg, and like I said, I usually start with kg being just enough to hold it at its position. So the way I would tune it is I would try some output and try to get it where it pretty well holds it. So 0.75 when it's all the way out. Let's see, what did they say we should use for G? 1.75, yep. And then now we can use some different set points, 1.5, and we see it doesn't get there because we still have a P of 0. So we can try a P of 2. Now we start to get there, we start to move there. And if we go back to 0, it holds it. We go to 3.14, does a pretty good job getting over there. So on an arm, we usually use a cosine. So when it's straight up, this G value is 0, and when it's all the way out, it's 1.75. So as it moves up, the feed forward gets lower. All right, does that make sense? And why it helps us a lot with gravity, with mechanisms to get smoother motion? Like in our second year of FRC back in 2019, we had an arm that pivoted and we didn't know about feed forward yet. And so like at the very beginning of the match, we would just run the motor a little bit and then let the arm fall. And then when we came up, we kept slamming up and we repeatedly broke the hard stop on the top because we kept slamming into it. And now feed forward helps us a lot with that. Yeah, question?
Gives a bit of slop when you move arms especially.
Mm-hmm.
So are you able to try and adjust it out here, or do you usually have another series of little offsets and adjustments for that?
Sure. Yeah, the question is, does feed forward help you with some of your lash or slack that you have in your mechanisms? So like our arm, our first year especially, you could probably grab it and you could move it this much, right? It doesn't really help you with that, no. Advice I would give is probably make sure your sensor is sensing your arm, not your motor. So a common thing is use the motors or the sensors that are built into the motor, right? Well, it won't pick up any of that lash. So it'll think it's at the target even though maybe it's at this side of the slop or it's at this side of the slop. So put your sensor on the arm and it then will know, but you still will run into that, right? Like you might get to the top and it pivots over a little bit.
Well,
but your PID would catch that and help move it back.
It doesn't detect because it first slops a little and then it meets its normal friction. I mean, can you compensate for that with the same kind of scenario?
Yeah, really your PID is what would help you detect that slop. Yeah, because it's more, feed forward is about predicting the motion that it's going to make, and you're not really going to predict that that's going to happen. But feedback, your PID will detect that and then react to it. Yep. So, I mean, obviously, the best advice is try to minimize the slack that you have, right? Yeah, but and make sure that your sensor picks it up, because otherwise your PID can't react to it. It can only react to what it can read.
Well, I think we've had scenarios where you have the robot gets jerky trying to make those last compensations because it doesn't quite settle before it makes the adjustment.
Oh,
So it's
sure.
already trying to compensate for being off, even though it hasn't really settled into where it's at when you're trying to move quickly.
Yeah, yeah. There's not a lot you can do about that. Your D could help a little bit, right? Because it would help with your rate of change, but it's not actually controlling that.
Right.
It's happening by the mechanism by itself.
So it really comes down to just working mechanically sound on that kind of slack.
Yeah, yeah. And then your PID will react. It, like you said, it does ultimately end up doing it. It catches it. It just doesn't catch it as fast, right? Because it doesn't know that that's going to happen. Yeah. All right, so a couple other feed-forward terms that we use are KS and KA. KS is static friction. So if you have taken basic physics, they have, like you do an example where you put this block on the table and you use a scale and you pull on it, and you find that it takes more force to get it to start moving than to get it to keep moving. And KS is just used at the beginning when you start from 0. It adds on a little bit of output to get it to start moving. So it helps overcome that and can help you get to your target a little bit faster, or especially if your mechanism has a lot of static friction. A lot of our mechanisms don't, but sometimes that is a bigger problem. And then KA is how much output does it take to accelerate the mechanism. So KV was how much does it take to hold at a speed. KA is how much does it take to get it to move at a specific rate. And then motion profiling is where we get into PID just rushes to the target, right? So if you're far away, you have a large error, you multiply it by P, and you just start moving at full speed. Motion profiling will do a plan for the whole motion, and it will do a smoother acceleration. So this is our position over time of the mechanism. And if it were just PID, we would see our position starts to move faster at the beginning and then slower at the end like that. But our acceleration would probably be larger at the beginning, and then it would just taper smoothly. And our velocity really is the big one here. Our velocity with PID would race to the fastest velocity and then slow down as it got there. Motion profiling helps us do this profile where we speed up, we cruise at a speed, and then we slow down as we reach the target. And that really gives you like a lot nicer looking, especially like on an elevator. It really looks smooth and nice, but it also helps minimize wear and tear on your mechanisms because you're not always like going straight to applying 100%. And it can help with things like lash too, because if you start really fast, maybe your mechanism lashes more. You can limit your acceleration and you can limit your max velocity, which can help with that. But it actually plans out the whole motion, both the velocity that the mechanism is supposed to be moving and the position that it's supposed to be in. And then every time slice, so like on the across the road electronics, the Krakens or the Falcons or the Spark Maxes, they have a loop that runs every millisecond and looks at how fast is the mechanism moving and what position is in, and applies PID to both of those to try to follow that smooth curve right here. So even if I'm doing position movement, it also plans and does PID around the velocity. So you can get a lot more accurate targeting too, because you don't kind of wait until you get close. You start planning right away and then start correcting. So if it's moving really slow, it'll start correcting over here and try to get back on that target. And you use both feed forward and feedback with that. So you can use all of your gains, PID and KS, KG if you're using something with gravity. So yeah, we already talked about why would we do that, because you get smooth motion, reduced wear and tear, and it increases your accuracy. So there are several different ways that you can do that in FRC. If you're using smart motor controllers like the CTRE ones that we talked about, or rev mechanisms, or I think they might be the only two that have them. The other, the latest ones don't have it quite yet. But it's called Motion Magic. They have a brand for it in CTRE, and Rev calls it Max Motion. Rev used to have a Smart Motion. I'm not sure if that's been removed this year. That one didn't work as well. Max Motion now does both planning of velocity and position. And then you can also do it on the robot. WPI Lab has a trapezoidal profile built in, and it's just like how you can run PID in your robot, you can run it on your robot. The reason I would use the smart motor controller instead is because that loop is 1 millisecond. On your robot, that loop is 50 milliseconds. But also, it's closer to the sensor, right? So if you're going to use the sensor that's on the motor, it has very little latency for how long it takes to get the data. Where if you're running it on your robot, it has to come across the CAN bus and look at it and then evaluate it less often. So always prefer using a smart motor controller's built-in capabilities if you can, but running it on your robot works as well. Yeah, question?
So if you're running both the CTRE product and the Rev product on the same system, is there a problem with running both Motion Magic and Max Magic both?
Sure. So yeah, the question is, on the same robot or even the same mechanism, could you use CTRE and Rev products? You probably wouldn't try to use them together. So like, let's say you have an elevator that takes 2 motors to lift it. You probably want those 2 motors to be the same. You probably don't want a Spark Max and a Kraken. But like a swerve module would work fine, because you have one that's doing movement of the wheel, along the ground, and the other motor is doing motion side to side. So they're working completely independently. So yeah, you could definitely do that. And that's a great use of motion profiling, is the azimuth control on your swerve module, because you'll get more accurate output and it won't be as jerky, right? Like we hear a lot of those SDS modules going ting, 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 ting. It'll help with that because they will have less, quick motion like that, but they'll still be very accurate and get to the target. Any other questions? The question is, are there other profiles? There are. I don't think WPI Lab has anything built in. CTRE does have some more capabilities, and they have the ability to tune the trapezoidal, like the curve, the S curve. So they have an S curve one, and you can tune that. So there are a couple other options. Trapezoidal is the most common, and it's pretty simple to understand that, it accelerates, it cruises, and then decelerates. But yeah, absolutely, there are other options too. Yeah. Any other questions? That's the end of my presentation. Yeah, question.
With PID, how do you compensate for being able to, how do you make the robot track the target with pretty high accuracy without having like super wild gains when you're farther away from it?
Okay, yeah, the question was, how do you tune your mechanism with some pretty good accuracy without having it run out of control when it's far away? Is that?
Well, like being able to stay on your target with very small, like adjustments, or like if your robot or your arm gets pushed just ever so slightly, being able to track back to your target, but still function in the same way when you're really far away from it.
Sure. So yeah, how do you, very small adjustments, how do you get it to make small adjustments but still react quickly? That really is tuning. Your p-value is going to be your biggest thing there, right? When you're close, you need to have a small p-value, or a small correction, right? So your p-value is multiplied by your error for a small correction. It's going to be larger farther away. Feed forward would also help you with that some, because you would know as soon as you're off, you know you need to apply some additional output. But yeah, if you get your p-value too high, then you're going to oscillate around the target. So it's always it's a tuning exercise to get it to react as fast as you can and try your different output positions that you're expecting. So like on that one, we kind of showed, well, it worked well when it was over here, but when we had it over there, it didn't work as well. Yeah, really just a tuning exercise. Any other questions? This barcode here will take you to our website where we have the slides. I think this is going to be on YouTube as well. So, yeah, another question. So the question is, when you're using the WPI Lib trapezoidal profile, what's the best way to tune it? I always start by tuning my PID first. I guess I don't have an example of that. To tune my PID first. So I start with my feed forward, if I'm going to use feed forward, try to get good behavior with my feed forward. Then I add PID and try to get to a smooth output. And then there's really only two other settings on the trapezoidal profile. It's your max acceleration and your max cruise velocity. So now you're pretty close. So I would then, like say it's a CTRE one, I would hook up the Phoenix X and I would look at the graph and figure out what are my velocities that I'm getting and what acceleration am I getting. Because that's really hard to kind of figure out in your head, right? Like, or without any real data. Their graphs give you great output, and then you can take a look at those values and say, this is what I think I want, and go plug those in. And then, yeah, so it really just has those two additional parameters. Sometimes you'll tune those, and then you'll want to adjust your PID or your feed forward a little bit more, but that's the order that I do them in, and it really helps. Any other questions? Any other experiences anybody wants to share with motion profiling or anything else? No? All right, well, that's all I've got. Thanks. I'm Andy Gosser. I'm a mentor for 7028. I had 2 kids go through our program. Now one is in college, one has graduated and is working as a software engineer. I do programming and control systems with the team primarily, and I'm a control systems advisor at some events. I wear the orange hat, come over and help you guys when you have trouble. I'm going to be at Granite City this year and at Great Northern, and maybe at some of the off-season events too. And I am an SCSU graduate right here from St. Cloud State. So at a high level, we're going to talk about dashboards, how to use them, some of the different options that you have in FRC. And then logging is one that a lot of teams don't do. So we're going to talk about why, how to view them, and how to do that in your code. So what is a dashboard? A dashboard, it displays data during the robot operation. So there's some other tools that we use for other things like Phoenix Tuner, or Tuner X it's called now. We connect it to our robot, we can see what's happening in real time, but we don't use that during a match. A dashboard is more for seeing what's happening right now and that you would maybe use at a match versus a debugging tool like some of the other tools. So it can show, whatever you put on your dashboard. A lot of things that you put on there are sensor output, camera streams. Sometimes you just want a driver cam, or sometimes you want to be able to see in an area that you can't see. You can put a stream on the dashboard. Any other meaningful robot state? Is my robot ready to shoot? Do I have a game piece in the right position? You could put that on your dashboard to help your driver. And you can also input values. So the first thing that people usually use dashboards for is, I need to run 2 different autos. How do I pick it when I start a match? So we'll usually put a chooser on the dashboard that the drive team can choose. The dashboards send data over something called network tables. It's built into WPI-Lib, which is the library we use to build our robots. And it makes it really simple to transfer data back and forth between your dashboard, but we also use it for coprocessors like your Limelight or other mechanisms that you want to be able to talk to. And you put data onto them, and then you can display it, but you can, your robot is the server, and then you can have multiple clients to it, and they can talk to each other. And it simplifies that a lot for our programming perspective. So there's several different dashboard options in FRC. The one that a lot of teams have been using over the years is Shuffleboard. That one is getting deprecated this year because nobody's been maintaining it, and it's gotten kind of out of date. So it will still be included with WPI-Lib this year, but not after that, probably. Smart Dashboard is an even older one that hopefully teams aren't using that much anymore. Last year I had that one crossed out already, but it is still included with WPI-Lib, and you can still use that dashboard. But the primary ones to use now are Elastic, FRC Web Components, and Q FRC Dashboard. So we'll dig into each of those. Elastic was new a year or 2 ago now, but it's now built into WPI-Lib. Last year, that was the first year that they built it into the installer. So you don't have to do a separate install. If you want the latest version, you might have to go grab the latest version, but it will be included with your install of WPI-Lib. And it's becoming more popular. I think this year it's going to probably be the top choice for dashboards. It has a lot more modern user interface than Shuffleboard or Smart Dashboard, and it uses less resources, which is something sometimes you have to worry about on your drive station because it's taking all your joystick inputs and sending that to your robot. You don't want that to be overburdened. And I found it to be a lot more reliable than Shuffleboard, especially the last couple of years. Shuffleboard hasn't been maintained very well, and we had a lot of trouble with it disconnecting, not staying connected, or using a lot of resources. So there's a link there where they kind of made the announcement of Elastic a couple of years ago, and then some of the new capabilities. But this is basically what it looks like, and you can have a camera stream going here. That's what they have in the example. FRC Web Components is another pretty popular option. It's not included out of the box with WPI-Lib, but it's a separate install that you can go download. And it's web-based is kind of its advantage, is if you want to be able to create your own widgets and you know how to do some web design, this would be something to look at. It actually is like a little web app that runs that gives you a nice dashboard. So I have a link there if you want to get more info on that. The question was, is there any issue with it being on the network during gameplay? It actually, the web server runs on your computer, not on your robot. Yep. And then QFRC dashboard is a separate one. That one is also a separate install. It was new last year. And what they really say is that it's less resource intensive on your laptop is one of their big things, but it also has extensibility to create additional widgets. I haven't seen a lot of teams using this one yet. It was new last year. It might be worth exploring. So shuffleboard is one that was pretty common. This is our picture from 2019, what our dashboard looked like. We had a stream of the field there, and then we had various things that were showing up. You could choose your autonomous mode. I think it had a couple different drive schemes or something that you could select, and then helped you kind of see some Limelight data. It is still built in, but it's deprecated, so I would start moving away from it unless you have a library of something that you love and want to keep using it for another year. And it's really not aging well, uses a lot of resources, and we had connection issues with it. So how do you choose a dashboard? I would say if you have some time, try them out and see which one you like. If you want to have something that's a little bit more extensible, maybe you want to look at the web-based one. If you want something that's just built in, I don't have to worry about installing multiple things, don't have to go get an install from anywhere, then probably Elastic is a great one. And it never hurts to kind of talk to other teams and see what are you guys using if you want to get a little bit of their experience too. So yeah, let's take a look at what does it look like. So I need to get my stuff here. All right, so this is the FRC WPI Lib Visual Studio Code. And you can run a simulator, and that's what I'm going to do because I didn't bring a real robot today. And hopefully this all works. Sometimes it doesn't. I have the wrong project open. Sometimes it doesn't work when you're on separate Wi-Fi or whatever. So for a demo, it's a little scary, but we'll try it. So this is our robot code from our 2025 robot. Doesn't really matter what code I'm running, but we're going to pretend we have a robot. And then I'm going to open Elastic. This is the 2025 Elastic that's pre-installed. Just waiting for the simulation to start here. There we go. All right, this is the simulation interface. And then here is Elastic. So right now I have Elastic open, and it says it's connected. So it did find my simulation and connected to it. And I have, within my robot code, I have some dashboard set up with some widgets. So I can choose to download it from my robot. And I'm going to pick this as the one I want to download. I want to fully overwrite it. And so now I have some additional tabs. The way Elastic works is you come in here and manually set up your widgets. So you'd be like, oh, I want to put this here. And you drag it on. And then once you get everything set up the way you like it, you save your layout. And then you can just save your layout on your driver station and open it, or on a different computer, and you can just open that file. You can also put it on your robot, and it will be served on a web server. So that's what we did. We had it on the robot, and I could say download from robot, and it gives me the choices. That was a new option last year, and it was a pretty cool way to do it versus you used to be able to build them in code, and that was a little bit harder to do. So this is our dashboard. I don't have the actual robot, so I don't have the camera, but we had a camera that was pointed into our climb area so we could see if the cage was engaged. So this just looked inside of our robot the whole time for the driver to be able to look at. Over here, they could choose the autonomous that they wanted to run. If you want to run no auto or one of these three that we had chosen. And then the driver had the option to select, I don't remember what the controls are, had the option to select, do I want to score on level 4, level 3, or level 1 of the reef? Our robot wasn't capable of level 2. So this would show just some feedback to help them know which mode they were in. And then this one here was a debug one that we had, that if this big box isn't green, don't leave the field and let the match start. Restart the robot if this big thing isn't green. So it's good for stuff like that. Like, just make sure that your robot starts up and your drive team is out there trying to hurry. Give them some big things to look at to say, is my robot ready to go? And so if this was red, the drive coach would be like, no, restart the robot. And so then they could restart it. Any questions on Elastic or this demo so far? All right, so that's what dashboards are for, mostly for your drive team. They can also help you in the shop. So like we did have some additional tabs here that our drive team would never use. So this was like to run our tuning routines, and this one was our test mode. You could click run test mode in test mode, and then these boxes would individually turn green. And you could click this button to take the arm in and out of brake mode. So if I want to be able to move the arm, I could put it into coast mode and more easily move it. But the drive team would use the driver tab. So logging is a little bit different from a dashboard because it stores your data over time. And you can save that data to a file on your robot, and then you can look at that data after the match, which is really helpful. So for debugging when you're trying to figure out what was going on. So you can automatically log all network table data, which is cool because this is all network table data. So all of that, you can just automatically log it, and you can go back and look at that afterwards. So you can see, oh, the driver had this level selected, and this is where the robot thought it was on the field. All of that would happen automatically if I'm sending it to the dashboard. And all of my data from the coprocessor. So if I have a Limelight, which is a camera that you put on your robot that looks at targets, it sends its data over the network tables for the robot. All of that data would get logged automatically too. So, maybe your robot was misbehaving, you can go back and look and see, well, did the Limelight see a target? Did the driver do what they said they did? Yeah, question?
So with that, quick questions. One, is it only logging during a match, or could you set up there, like when you're trying to work on problems, you're troubleshooting in your room back at your station, can you set the logger till turn in and log all the data and just randomly running around and save that data? Is
Yeah.
that possible?
Yeah, the question is, does it only log during a match, or can you also have it log in the shop or any random time? And if you use this data log manager start, usually you just put that in robot init, it will always log. So you can put a little USB drive into your RoboRio. That is definitely advised if you're going to do logging. Then it will automatically put all the logs onto that USB drive. And we have like a 32 gig drive, and it was enough for like the whole season worth of logs. And it will do it, it'll put like the time in there. It will sync the time with your laptop, so it'll know what day it is and time, and it'll put that in the log file name. But if you're in a match, it will actually name it based on the match. So it'll be like Q37 for qualifier 37, and it has the event code in it. So when you go back to find the files, you can see the ones that are from matches versus just like the random ones when you were, who knows what you were doing.
What the timestamp from the laptop that's hooked up to the driver station while you're running around saying shop, it was based on that timestamp?
Yeah, the timestamp from your laptop always syncs with the robot. That's part of the network tables capability. It syncs the time on your robot, so then all your log data can be, your log file name is what I'm talking about. But yeah, all your data can be synced back to real time, not just the time that since the robot started. Yeah. Yeah, so this data log manager start is a very simple way to just start logging. If you're not going to do anything else, you're not going to think about it, you don't know what you want to log, you just know that it would be really nice to have some logs. Just do that. And you don't ever have to think about it again if you've stuck a USB stick into your RoboRio. If you didn't put a USB stick in your RoboRio, you might run out of space at some point. So it will automatically delete the old logs, But when the Robo-Rio starts to get low on space, it doesn't get very happy. So it's probably a good idea to do that. It does delete the old files automatically, but not until the drive gets pretty full. Yeah, yeah. Yeah, and then you can log custom values, whatever data you want to log with the data log manager and the data log. So there, go look at the WPI Live documentation on how to do that. But if you have data you're not sending over the network tables that you want to log additional data, that's a simple way to do that. So then, what do I do with the logs, right? Advantage Scope is a really awesome way to view your logs. Advantage Scope was developed by the team Mechanical Advantage, and they've been adding stuff to it since they started it. Last year it was included with WPI Live, and it will be again this year. Again, if you want the latest version, you might want to go get it from their website, but it's great. Like every driver station that has WPI Live installed has it on there, right? So like as a CSA, I'll come over to a team, they're like, I don't know what logs are, and you're like, well, you already have Advantage Scope, let's go look at it, right? So it's great that it's just built in, you don't have to think about it. You can view your data live. It'll connect to network tables, so like a dashboard, and you can see the data live, and you can edit those values on the network tables, but you can also play back logs after a match.
Is there default logs that are already grabbed, or do you have to run the data log manager in order to add in all those logs? So say we have CSA come show up, they're like, I can't help you because you didn't put stuff into your manager, or is there stuff already defaulted in there that as long as we tell it to log it, it's there?
So yeah, the question was if we didn't add any additional logging, would there be logs already? So if I call a CSA over, will they be able to help me? As long as this data log manager start is in there, it will log all the network table data. And then it also logs like some of the driver station data, but we'll talk about how to get additional driver station data. But yeah, so I mean, the first thing is do this. I don't know if that'll be included in the template this year or not, because if they put it in the template, it might start filling up Robo-Rios and people don't expect that. So you do need to potentially turn it on. But another cool thing is you can log the driver station data. So you can get the joystick or Xbox controller inputs. So this is a really great line to add to your code. Driver station, start data log manager, get log. And then when they come back from a match and they say, I pushed the A button and the robot didn't do what it was supposed to do, you can pull up the log and see, did they really push the A button or not? And it's really cool. It looks neat when you play it back and it's everything's moving. So we'll do a demo of that. Let me close the simulation. Or I'll close Elastic. Actually, we'll connect to the simulation just to show that too. So this is Advantage Scope. It's included with WPI Live now. Advantage Scope WPI Live, this version. You can also install it separately if you want the latest version. And then in this file menu, which is probably a little bit small, there's some options to connect to the robot or connect to the simulator. If you've configured your team number, you can just do connect to robot, and if you're on the Wi-Fi with the robot, it'll connect to the robot. I'm going to connect to the simulation because I have that running. So here, the simulation is sending some data, and I've got all my network table data over here. And so I can expand these out and look at the data that it's sending over. And I can also click on this little thing. It looks like a settings icon, but this is the edit button. If you click on that, now I can edit some of the values. So we used that this year. We had a little tune arm function. We wanted to try different angles and heights of our arm mechanism on an elevator for scoring. And so we could just type in here, like, I want to go to an angle of 3.14 pi, and I want to go to a height of 1 meter, and then they'd push a button and it would go. So to increase that cycle of, I need to do some debugging and I want to see how it works, you can have this reading network table data, and then you can edit it in real time. So I'm going to actually try to enable the robot and drive it around. We'll see if that works. Yeah, okay. So I can actually enable the robot, and I have an Xbox controller, and in the simulation I can drive it around. So this is using odometry, simulated odometry data, which is how fast are your wheels turning, what direction are they pointed, and then the red arrow and the blue arrow are my swerve module states. So the red is where my swerve module actually is, and the blue is where its target is. So both the angle and the speed. The longer line means the target and the actual velocity are higher, and then the rotation is what direction are they pointed. If you use Path Planner for autonomous, you can Path Planner automatically adds some data to the network table, so you can have it do that. I'll show you a log of that. This is kind of a similar view to what we had with those lines for your swerve modules. This gives you some additional data on rotation of where your swerve module is and where it thinks it needs to be, and then your distance. So like without having to watch it drive across the field, you can have that data. Joysticks is for logging. The 3D view is pretty cool. You can get a 3D view of the field, and then you can move around on it. And as I'm driving around, it also shows that data, which is kind of neat in the sim or in the shop, but it's really cool when you play back a log. So let's open up a log and we can look at a couple of those other ones. So it has an option here to open logs, and then I have some logs from our last season. So I'm gonna go to one from champs. I'm just gonna do qual 37. So it's really small, but you can see here it says Curry, that was the name of the event, _ Q32 or 37. That's our qualifier 37. And then I want to get to the WPI live log. So we'll talk about these hoot logs a little bit too. Those are from CTRE, from the devices. So I'm going to put that down, and I'm going to stop the simulator. All right, so this is a log from one of our matches, and there's a bunch of data at the beginning here where the robot's just sitting there. That's when the match was getting set up. And then this green bar here is autonomous, and then it was disabled temporarily in between, and then this is all teleop. So I can say, let's go to the beginning of autonomous and just play it. And I can see the robot driving around on the field, and I can move around and watch what's happening, which is pretty neat. Match time would be part of your driver station data, I think. Yeah, I think so. I'm not positive though, but it does tell you, up here when the robot was enabled in autonomous and teleop. But there is a feature that I was able to demo last year, but when I went to try to demo it, it didn't work. That was my favorite feature to demo. You load this up and you go to the video tab. We'll try it today. And you click on this Blue Alliance button, and it's supposed to go to Blue Alliance, find a video of the match on YouTube, and then it will sync it up match time based on that bar on the bottom. And you can actually watch the video of your robot while you're doing the data. If I had a match video, I could also use that. We had a little 3D camera on our robot, and we exported some of that data and then synced it up because we had some trouble. The arm isn't doing exactly what we think. So we could look at the arm, sync it up in here, and then open up multiple tabs and kind of see what it was doing compared to what the video showed it doing. So if you could sync that up, you could get the match time from the bottom of the video. Yeah, it was where I was going with it, yep. So this is that Path Planner view. It's more useful when we're actually running Path Planner. So the green there shows the path that it's gonna drive on, and then the red ghost is where is Path Planner telling the robot to be, and then the blue is where does the robot actually think it is. So like after that path runs, the robot moves a little bit, but it tracks really well with where it's supposed to be. So here it's trying to score, and then this is all a path. And then at the end of this path, now it's trying to score and the robot's driving by itself. So it drives off of that path. But that's really helpful. Like you run your auto and you're like, it really doesn't doesn't look like it did what it was supposed to do, it's helpful to go back here and see, did my robot think it was doing what it was supposed to do? Because if it thought it was doing what it was supposed to do, it might be like your wheel diameter is wrong or something. But if it knows that it wasn't doing the right thing, then it might be tuning. It might be a PID thing, or your path might be faster than your robot can run, something like that. So this is a really helpful tool when you're using Path Planner that, was nice that it just automatically sends that data over network tables. And so if you log it, it gets saved automatically. All of these, record their data so you can play this back. And here we should be able to see joystick data once we get into teleop. Yeah, so here we use actual joysticks. And so here he's pushing button 1, here he's moving the sticks around. So like if he said, I was trying to score and I was pushing button 2, you can go back and confirm that that's what he was actually doing. If you use an Xbox controller, you can choose like Xbox controller blue and it shows a little animation of the controller. 3D field does the same thing. And then we had an arm on our robot, and this, we sent the data over the network tables for the mechanism, and then it automatically gets logged, and this has a visualization of the arm. So you can see the elevator moving, that larger bar, and then the arm on the elevator moving. It's just the sensor data. So they're auto-ended, now it's just falling on its own, driving around. So we could match that up with what we were seeing in our 3D video. Kind of where did it think it was? What was it doing? And then we had one other thing where we had some sensors on the front of our robot, or on the side actually, and when we scored, we try to look at the reef and get our distance set right. And sometimes it was weird, like even in this log, you saw that on the second one where it scored, it kind of twitched and like moved around a little bit weird. Maybe we were getting some bad data from our sensor. So because we were sending the sensor data over the network tables, it got logged. So you can drop all that sensor data on here, and then you can drop on whether the robot was enabled or not. So you can see across the bottom, there's this true, this is autonomous, and then it was disabled, and then it's enabled. And so you can go to any point, and you could line that up with your video or with your other data to kind of see, well, what did the sensors see? Was the robot reacting to the sensor, and the sensor data was bad, or was the robot misbehaving? Sensor data was great, but the robot was misbehaving. So any time slice data you can put onto one of these graphs. All right. Any questions after that demo? Yeah, question.
Do we know yet if this will work still with the system core, since this is the last year of the actual Robo-Rio?
The question was, will this work with system core? I don't have any official knowledge of that, other than kind of what I've heard. But system core is still going to use WPI lib. I would certainly expect that it's still going to use network tables, and that most of this is going to work the same, because that's all like foundational WPI lib framework stuff. Doesn't really have much to do with interacting with the hardware. That's the part that's going to change. So I know like the reason that they're maybe deprecating some of these older ones is they need to free up time to go work on system core. But other than that, I would expect this will all still be very similar once system core is out. Yeah, system core is the new control system for anybody that doesn't know. Yeah, go ahead. Maybe you have some knowledge. 4607's on the trial.
So yes, so system core will optimally function the same way as the Rio. It's just a different hardware platform. So like the firmware is going to be different, obviously, but everything you're interfacing to it will remain the same. So like right now, you can technically run the Rio and system core parallel, and they'll do everything that they can do, except the system core going forward will support FTC and FRC, and it'll also allow you to do onboard wireless. So instead of having to like connect your robot radio, you can connect to the system core instead, and then you have like
For FTC especially, yeah. Okay, yep.
So yeah, it'll be able to do everything. It'll just be that because it has enhanced capabilities, I'm sure they want to deprecate some old stuff and bring new things to it. So that's part of it too, is because it's running a Raspberry Pi CM5.
Yeah, for the stream or anybody, they couldn't hear. The short of it was, yeah, the software should remain essentially the same. The interface is the hardware, and you can potentially run them kind of side by side. Yep, the interface would stay the same. Yeah, other question?
So I noticed you had like models and stuff in your simulations and in the Advantage Scope logs. How would you set those up, or what do you need to do to set those up?
So yeah, the question was the models in the simulation. So are you, like when I was driving the robot around and it was able to drive?
Yeah, that and then the 3D one and the arm, like one of those.
Okay, yeah, in the simulation, the driving around, we use CTRE and their foundation, as well as like Yagsel, they have their sort of, they have simulation support built in. So I didn't really have to do anything to be able to drive the robot around. The ARM, there are simulation capabilities built into WPI Lib. I didn't really use those. I just used the mechanism and use the actual data. So I can't simulate the arm. I did get the arm where like you push the button to have it move to that position and it just instantly pops there in the simulation, but I didn't have any simulated physics.
So the arm's just the data you got from the match?
Yeah, when we were watching the arm move, that was actual log data from the arm actually moving on the robot during a match. Yep, yep. Yeah, another question? Yeah, the question is, can you have different 3D model states for the arm? You absolutely can. In this 3D view in Advantage Scope, I imported our robot from Onshape. They have on their website how to do that. You can export it and then import it, and you have to just kind of get it set up so that it doesn't float off the ground sideways and stuff. But you can break up the model into multiple pieces and put those into Advantage Scope. So like my arm would actually move on here. I didn't have the CAD skills to do that, to demo it, but you can definitely do that. And this will also do the 3D mechanism. Like if I go over here, this is on Smart Dashboard Arm was where I put it. At one point I did have it working where it would have just like a big chunky arm. I don't know if it'll work or not. Yeah, I can't drag it on there. But I did have it working at one time where it was just like a bunch of blocks that were on top of each other and it would move up and down on this 3D model. You can do that stuff in Advantage Scope. And if you have a Apple device, you can even use XR and you can like look at it happening on the floor, which is really cool. I haven't tried that. I don't have an Apple device. So, any other questions at this point? All right. So another way to log data is Epilog. It was new last year in WPI Lib, and it makes it a little bit easier because I don't have to write either any or very little code to be able to log some stuff. You use this annotation @logged, and I'll show what our code actually looks like with that in a little bit. But you add @logged to it, and it will automatically log the data from that class, all of the fields. It will log them all. So it's really easy to set up in your robot. You need that Epilog bind this, and in your robot container, you put the @logged annotation on it, and then on any subsystems or commands that you want to log, you put @logged. There's ways to tune it additionally to say I want to log these fields or not log these fields, but if you just want to log a whole bunch of stuff, that's a really easy way to get started. The question is it resource heavy? It's supposed to be very little. Like it doesn't happen on the same thread in real time with the robot. It gets queued up and happens. But of course, it is additional processing. If you're running a RoboRio 1, you might want to keep an eye on your CPU and just, make sure, just like always, if you're running a Rio 1 especially. So some other tools that you can use is the driver station log viewer. After a match, all of the driver station data, like when you're running a match, you'll see a bunch of messages coming by. all of that does get logged on the driver station itself. So that's one of the first places as a CSA that we go look is just like, what's in the log? Because it'll log the voltage and some of the output data. And like if your robot just completely crashes, that will usually end up in there, the stack trace that tells you the robot crashed on this line. So that's a great place to just start. Like my robot didn't work, what happened? Go look at the driver station log. And then there's the Rev Urkel, unofficial Rev compatible logger, and TunerX. Those are both for vendor libraries. CTRE has TunerX. They have a logger that will automatically log all of the data from your from the CAN bus, essentially, from all of your smart motor controllers. So it'll log all of the data that it's sending over the CAN bus, position, velocity, everything that it's sending, everything that you can see in TunerX will get logged. Rev doesn't have that out of the box, but Mechanical Advantage created this Rev compatible logger, so you can put that in your code and it'll do the same thing, where it logs all of that data. You can open it up in Advantage Scope and view it afterwards. And then TunerX and the Rev hardware client, those are both things that you can use in real time with your robot. You can connect them to your robot and move your mechanisms, see how they're behaving. You can do graphs over time. So like if you were in my previous session, we talked about velocity control on a flywheel. How fast is my flywheel moving? How fast did it get to the target? Did it oscillate around the target? TunerX and the Rev hardware client are your go-to tools for that kind of thing, because you can connect to the robot, see what it's doing right now, and you can actually control the devices that way too. So let's do another demo. My papers that I dropped here. All right. So let's take a look at how we can do epilogue. Try to make this bigger. All right. Is that readable up there? I think so. You guys see that somewhat? All right. So for epilogue, we have this epilogue bind this in robot.java. So just in the constructor for robot. Normally we don't touch this file much at all, and this is one of the cases where we would. It's just basic plumbing. Epilogue bind this, and then we said in our robot container, which is kind of our main place that we create all of our subsystems and commands, we have another logged annotation. Now on this one, I said I don't necessarily want to log everything. I want to be able to choose what I log. So I can put this strategy opt-in, and then it will only log the things that I put the logged annotation on. So it'll log my ARM subsystem, but the climb subsystem, that one didn't really have much for data, so we didn't log that one. And so then, like the mitochondria subsystem is one that had some logging too. The mitochondria is a little device about this big, and it just provides power to your vision systems. Yeah, we have a question.
For like the logging annotation, is that kind of in addition to like the IO setup that you use with Advantage Kit for all the logging?
The question was, is the epilogue at logged annotation, do you do that in addition to Advantage Kit IO? So Advantage Kit is a different tool than Advantage Scope. Yep, so Advantage Kit you can use, and it will log a bunch of data. You have to structure your code in a little bit different way with the IO, and then it will log all of that data, and you can actually play it back in your code. So that is kind of outside of the scope of this discussion, but that is definitely another tool to look at that has a lot of capability. If I wouldn't try to run it on a RoboRio 1 because you probably don't have the overhead, but it's very cool because you can record that data and then play it back in your code. And so you can debug, actually, like you can go into Advantage Scope and see, oh, my robot was doing this. Why was it doing that? You can go set a breakpoint in your code, replay it, and see what it actually did. But yeah, that's a deeper thing to do, a more advanced topic. So this @logged is built into WPI lib, and then it will log it into the WPI lib log. Yep. So Advantage Scope is the tool for viewing log data and network table data. Advantage Kit is that framework that you can use to build your robot on to get all that playback capability. Yeah, so the mitochondria subsystem, this one has that logged annotation, and we also did opt in because we didn't want to log everything. And then down here, we wanted to log this USB channel 1. So mitochondria has like multiple USB plugs that you can plug into it, and then it powers your devices. Well, I knew that my Raspberry or my Orange Pi number 1 was connected to that port. So I wanted to log its current as Pi 1 current. And then this would log it into the log as Pi 1 current, Pi 2 current. And my LEDs were powered by it too, so LED current. So this will now, every iteration of the robot, automatically log that data into the log. It won't send it over the network tables, but it'll log it into the log. Well, actually, it will send it over the network tables, depending how you configure Epilogue, now that I think about it. Because, yeah, we can see it in Advantage Scope. So, yeah, let's actually look at it in Advantage Scope. That was next on my demo. So, in Advantage Scope, let's say I want to look at that Raspberry Pi, or the Orange Pi voltage. I could create a new line graph, and then I'll go to robot, because that's where my top level annotation was. And then robot container was that next place that I had to put logged. And then these are all of my subsystems that had that @logged annotation on it. I wonder if I can zoom this. Yeah, there we go. And then you can just grab these and drag them over to left axis, right axis, and discrete field is like a true value field. So a true false value. So a lot of times what you'll put in there is the driver station data enabled to say, was my robot enabled? So then I can see where was the match happening. So on the bottom here is where it's, so then you can drag those over, and so like I have current over there, so it makes sense I could put all of my currents on the left axis and maybe my voltages on the right axis because the scale are way different. And then you can look at that. You can zoom in, you can scroll, you can, like the voltage and current of my output isn't that useful, but I also had like that ARM subsystem data that was in there and a bunch of stuff that is useful to be able to go back and look at. And it's very easy to get that log data because you just have to add those annotations. You don't have to do a bunch of coding. All right. How are we looking on time? Just about perfect. All right, so that was a lot. What should be your key takeaways? I think the key takeaway is enable that WPI live logger. So do data log manager.start, put that in robot, and it will automatically log your network table data. Just that alone is super helpful. Like that was awesome when we enabled that. It was like, wow, this is huge. And then that driver station data, that's neat and helpful. So you add that line to do the driver station data. If you're using CTRE devices, it's very easy. You just do the signal logger.start and that'll log all of that data. Or if you're using the CTRE swerve template, that's built in automatically. It's already set, already happening. That Urkel is another one if you're using Rev devices and you want to log that. That's a great way to do that. The question was, could you run all of these on the original RoboRio? These, I would say you can, yeah. Make sure you put a USB stick in, just for that storage purpose. But CPU-wise, that should be fine. Yep. All right. Any questions? All right. So this barcode takes you to our website where I've got the slides. It's going to be on YouTube. I'll put the link out there too if you want to share it with your friends. But thanks. Some of you have heard of that. I'm Andy Gosser. I volunteer with, or mentor with 7028. I've been doing that since 2018 when the team started. I had 2 kids go through the program. One of them is Brandon up here. He's now graduated and working as a software engineer, and my daughter is in college now. I do primarily programming and control systems with FRC, and I'm a control systems advisor. I wear the orange hat at events and come around and help when you're having trouble. I'll be at Granite City and Great Northern this year, and then probably some off-season events. And I am an SCSU graduate as we're here at St. Cloud State. So what are we going to cover? We're going to talk about what is localization, what is QuestNav, because that's what we're here for, why VR, a little bit about how does it work, just because I know everybody's kind of curious, how to use it, and we'll do actually a demo, if it works, of a setup and some robot code. So hopefully that works with our internet and everything here. So the problem that we're trying to solve is localization. So where is the robot on the field? So this is, our field over here. We want to know when our robot is here. We want to know our robot's there. The biggest reason that we want to do that is for auto. In autonomous, the first 15 seconds of the match, we probably want to drive around on the field. And so the robot needs to know where it is. But we can also use it for driver assist. So like if the robot is where it is on the field there and it's going to score on the reef, maybe we want to give the driver a button to push and it drives over to the reef. We need to know where we are on the field to do that. Or to auto align. So I know like if I'm in this exact position, I can do my scoring like to the reef last year would be a really good example. Or just aiming at the target. So 2024 was a shooting game where you had to shoot the discs. If you know where you are on the field and you know where the target is, you don't have to actually see the target. You can just do basic geometry and know the target is right over there. That's where I need to aim. So you can have relative or absolute positioning. And relative positioning is called odometry. And that's how far has the robot moved from its starting position. So if you know where the robot started, you can have a really good idea of where the robot is on the field. That's what QuestNav last year was great for. The other option is our absolute positioning, which is localization. That's where is the robot actually on the field. Not only where did it move since it started, but where is it actually now. So wheel encoder and IMU odometry is what we usually use for localization. That's how many, how much have my wheels turned and what's the rotation of my robot. The IMU gives us rotational data. It gives you a pretty reasonable estimate, but it has a lot of problems, right? If your wheels slip on the carpet, you get some variance in the carpet or tread wear. We actually found like if you drive one direction on the carpet, it reads a little bit different than if you drive the other direction because of the way the carpet falls, or certainly during an event, the way it wears, right? Sometimes there's holes in the carpet by the end of an event. And your IMU can drift. The IMU tells you what is your current rotation. Over time, that can drift a little bit. The modern ones that we have on FRC are really great for like the 3 minutes. They don't drift very much at all, but it still can happen, or you can get interference if you have like a motor too close or something. So the last few years, April tags has been something that we use to augment that encoder data, because April tags will give you absolute position on the field. They'll give you that localization. So you can look at an April tag, or ideally multiple April tags, and then it has built-in capability in the coprocessors and even in WPI Live to tell you if you saw those tags, you know where they are on the field, you can know where you are pretty accurately. But the problem with that is, like, what if another robot not blocks your camera, or if you have multiple cameras, it could still be blocking all of them? Or what if you're spinning really fast or moving really fast, the images will blur, right? Or they'll even be a little bit, there'll be lag, right? And if you're moving really fast, by the time you figure out where you are, you're not there anymore. Or what if you're out in the middle of the field and there's no tags nearby? So the Quest Nav gives us more like the wheel odometry, but even better. It's very fine grained. So think of it as a sensor that you're going to put on your robot. So this is the Quest, a Meta Quest, and it's an actual VR headset. You put this on your robot. And so here's a couple pictures. This one we had just kind of zip tied it onto our robot from the previous year and tried driving it around. This was a good position to put it in for working, but a pretty scary position to put it in if I was actually in a match, right? You're probably going to smash it. So on our robot this year, we never actually brought it to an event. We had some inconsistency and stuff that we saw, but we did some practice and tried to get it working. This was a great position for it here because it was protected inside of the robot, but it could still see everything that it needed to see. So Quest Nav is an app that runs on the headset. So it's actually like an Android device. There's an Android app that's running on the headset, and it streams the data to your robot. If you were in my last session, we talked a little bit about network tables. That's how it streams the data. It puts it onto the network tables, and then you can read that data in your robot code. And it has like millimeter precision. And it runs at 120 hertz. So it runs, very fast, which is, 120 times per second. And the cool thing is, like, this costs a little bit less than a Limelight, right? Because Meta has invested a whole bunch of money in it, and I'm sure they're selling it at a loss because they're expecting you to play games on it and spend money. That's why we say we're hacking it, right? So we're taking advantage of that. They bought Oculus about 10 years ago for $2 billion to get the start of this technology, and they've invested like $100 billion in it since then. So we get to take advantage of that, all of that investment, and put it on our robot for less than a Limelight. So how does it work? It gives us very accurate relative positioning. Maybe by kickoff, it will give us some ability to read April tags, but as of now, it only does localization. So if you know, or it only does like odometry, if you know where you started, which we usually do in auto, right? We're gonna choose an auto, we're gonna put the robot on the field where it's supposed to be. It gives you millimeter precision like throughout the whole match. But it's all based on where you started and that your robot was actually where you said it was when you started. So you can provide it a starting point either by where you placed it, or you might still want to use April tags for that. You might want to put a camera or multiple cameras so you can see April tags before autonomous starts and get an accurate position, and then set that as your starting position and then use Quest Nav from there. They might get to integrating April tags. There's some great advancements on that. They were kind of hoping to get it done over the summer, but haven't gotten it working yet. If they do that, they'll be able to fuse the April tag data with the Quest data, and you'll be able to get your actual location on the field. So how does it work? This is all theory, but like, we're all curious people. We want to know, how does it work inside? So it has visual simultaneous localization and mapping. So it has to figure out where it's moving, but it's also mapping the environment at the same time. So it looks for high contrast features, which, like, if I were to have it look around this room, it's probably going to find like the corners of the room and maybe the lights and some of the things that give very high contrast, and it'll pick those out and put anchors there. And then it looks for movement in those features. So like on our robot, if it's like at this height, it might actually see some of those lines on the carpet and use some of that to do its movement. And then it builds a map of that environment. So if you return to that same environment, it kind of knows where it is within that right away. And then there's also VIO. So this is kind of your eyes, what you see. And VIO is like your inner ear. If you were to close your eyes, you still know that you're walking around, right? You can feel yourself moving. And so there's an IMU built in that knows its rotation and some acceleration. And then it takes that data and fuses it together and does the mapping. So the IMU feels the movement, the camera sees the movement, and then it's fused together and confirm that, yes, we've actually moved. So it's all proprietary. They don't tell you much. Like some of the things that you might even want to know is, does it have an IR dot projector? Well, we don't know for sure. They don't say how it works. So when you're putting it on your robot, you can assume like all of these cameras that are all around it, you probably want to be able to see as many features as you can and as little of the inside of your robot as possible. So what do you need to do it? You obviously need a Meta Quest. The 3S is kind of the recommended one to use. The 3 is supposed to work as well. The 3 is more expensive. The 3S is cheaper. It was $250 or even less for Black Friday, and I think its regular price is $300. You also need a USB-C to Ethernet adapter with power. So just like a little adapter like this. On their website, they have some recommended ones. We got this one. The Cable Matters one is actually the one that they recommend. It does have to have power. And then a 3D printed mount. Several teams have shared their mounts. I think we used the one that Spectrum had done. You just 3D print it. Your headset, this part comes off and it pops in there, and you put a zip tie around it to hold it in. And you probably want power, because when it's running, like Reese asked me, how is this going to survive the whole demo? Hopefully it does. But you can put power on your robot, or you can charge it in the pit. But I would recommend power on the robot. So you could use like a mitochondria, or the Redux Redux is going out of business, but they made a little USB power unit, or Palalo has one, or even a USB power bank. You can just use like a phone charger. As long as it meets the requirements of the rules, you can put that on your robot too. Any questions at this point? All right, so we'll do a setup demo. Like, what do you actually have to do to get it working? So you have to create a MetaQuest developer account, and you have to enable developer mode. I didn't go into that in the demo. I've already done that. There's steps for how to do that. It's not very difficult, but there's a few steps you have to go through. You have to create an account, you have to activate it, and agree to the terms and everything. Then you go to setup.questnav.gg, and this is new, like just in the last couple of weeks, and it makes it very easy. Now I have this running. I need to first kill this. So you go to this page, see if I can make it a little bit bigger, and you just follow the steps. So the step number 1 is enable developer mode, then you connect it with a USB, and then you click Connect Quest. And there's a little pop-up here, you have to select it, and then hopefully it connects, yes. And in the headset, there's a thing that you have to accept. Everybody laughs when I do that. I don't know why. Okay, so now we're connected, and it's going to install the latest version here, 2025 2.1.beta. And you can click on this, and it shows you everything that it's going to do. It's going to figure out what OS it's running. It's going to disable the Guardian, which is, if you've ever used one of these, there's like a fence that you put around, and if you step outside of that, it gets mad. It disables that, turns on experimental features, turns off Bluetooth and Wi-Fi, so it's meets the rules of FRC, turns the brightness all the way down to save power, turns off tap to wake, otherwise you can tap on the side of it and it like gets weird in the wake gesture. And so it goes through all of these. When I first set it up, I had to do all of this manually. Now this website does it. So you just hit apply configuration, and it goes down and does those, downloads the latest app, installs it on the device, and I believe it even launches it now too. I was getting this demo set up, and I was like, oh, it got to the last step, installed. It'd be nice if it would launch it. And I put that in Discord, and like an hour later, he's like, okay, it's live now. So very cool to interact with them too. So it says it's installing. It takes a minute to send over the app. There we go. All right, all 19 commands executed successfully. So now, if I disconnect from that, I like to use this SCRCPY. It's a tool that you can download that allows you to, if you have a Android device connected over in developer mode, you can see the screen. Sometimes we use this in FTC because your robot actually has a screen and you can see it with SCRCPY. So now I can see inside of my Quest, and I don't see the app running, so it probably didn't launch. And one weird thing right now too is it turns the display all the way to 0, so I can't see anything in there. If I turn it off and back on, it puts it at 1. Then I can see in there. All right. So I'm gonna just launch it here. There we go. And it's a little flickery, but there, this is now the QuestNav interface up there. And so it's installed and it's running. And then because I don't have it on a robot, I need to do a little, oop, did I unplug it? Uh-oh, it crashed. That's the demo. That's how it works. Okay, so because I don't have an actual robot, I have to do a little hack here. I'm going to do ADB forward TCP 5801. If I had it on a robot and it was connected over Ethernet and my laptop was connected to it, I could talk to it over the robot network. But because I'm not, I need to set it up so I can talk to it over the USB debugging. So you would go to the QuestNav's IP 5801. There we go. So it is still running. And there's an interface now that you can configure it with. This is new over the summer, which is really cool. Like you can see what's actually happening and you can do your configuration without everybody laughing at you in the pit because you have the QuestNav held up to your face. So yeah, so there's the status here. It tells me I'm not connected to a robot, gives me what it thinks the robot's IP should be, some battery data, I'm at 85%. It tells me that it's currently tracking, it hasn't lost tracking, and it even gives the position, like every second it should refresh that. Maybe it disconnected, yeah. So the QuestNav tab is probably the first place you want to go once you see that it's connected, because you need to configure your team number, much like a Limelight or any other device. It needs your team number to know how to connect over the network tables. So you set your team number, and now you'll see, like, well, it didn't change. Restart. Yeah, after you restart, then it would try to connect to your robot at the right IP address. So there's some other things that you can tune here that you probably don't ever want to. You can set it to not automatically start. You can change the frequency. Like maybe your battery is running down too fast and you're like, I don't need to run it at 120 hertz. You can adjust that here. You can see the logs. So it logs all the data that the app is logging. You can see that right in this interface. And then you can change the port that this is listening on and some other settings in here too. For the most part, you just need to come in and set your team number and then you're good to go. There's also an info tab up here, which is kind of helpful, that shows you the version of QuestNav that you have installed, and then a little bit of information about your device too. Any questions about setup? All right. So yeah, we went through all this. We connected, we ran the setup, we did the app, we went to the dashboard, set our team number. So just in case the demo didn't work, had a couple screenshots. Demo worked, luckily. So then robot integration, you need to write some code to get it on your robot. The QuestNav connects to the network on your robot. So you know your robot's got a radio, it's got Ethernet, it connects to that. That's how the QuestNav connects to your RoboRio, sends the data over network tables. And then in the robot code, you choose what do you want to do with that data. So you'll need to install the QuestNav vendor dependency, That's how, like within a robot project, anytime we're gonna use a device, we usually have to install their library. You download this file from their GitHub, you put it into your vendor deps, and then you build the robot, and that'll download everything that you need to get it into your robot. And then we'll look a little bit at the code in a minute, but first we want to talk just a little bit about the coordinate system, because this is something that a lot of teams don't have quite right when like their auto isn't running right or they don't see things working right. Especially with swerve, this is something we spend a fair amount of time as a CSA making sure is right. So in FRC, forward is positive X. A lot of people think it's going to be positive Y, but it's not. It's positive X. And then left is positive Y, and rotation is counterclockwise positive. So it's a little bit counterintuitive. A lot of people think it's going to be like Y forward and clockwise rotation. It's not. It's X and counterclockwise. And then if you layer on 3D, because the Quest will actually give you 3D data, Z is up, and then pitch and roll are pitches around the Y-axis, so tilting back or forward, and roll is side to side. And then they're all, if the axis is pointing toward you counterclockwise, rotation around that axis is positive. So let's try to actually run it in the simulation and kind of see what happens. So I have to proxy another port so that the Quest can connect to my laptop. This would happen automatically on your robot network, but because I'm not using a robot, I need to do this. 5810. Proxy. Reverse. It's not proxy, it's reverse. There we go. All right, and then we need to configure the Quest to connect to my laptop instead of trying to connect to a robot. So on this general tab, there's an option here to say, where is the server for my network tables? It's gonna try to connect to a robot. I need it to connect to my laptop. So if you do this, it now is like, oh, you have this override enabled, because it's not going to try to connect to a robot. And then I'm going to run the simulation. This is our code from last year plus a little bit of Quest code, Quest nav code. And hopefully everything will connect. So I should see Quest nav show up here. Maybe I have to restart it. Yeah, let's try that. I don't think so. Make sure I typed that right. Make sure I typed that right. 5810. Yep. This worked at home, of course. Let's see if it works on here. So it doesn't look like it's connecting. I think it went in the background. There we go. Okay. It was in the background for some reason. I think there was an issue. There we go. Now we've got it. Okay, so now it's connected, and in my simulation, I can see I have a connection to the robot, this device called QuestNav. And so in here, I don't think I can make that bigger, but this interface automatically follows around because the robot's going to be driving all over the place and you need to be able to see the interface, so it follows you. It gives you the X, Y, Z position and rotation in real time. You can also configure your team number there, and that start up on Robot Boot, and it tells you here whether you're connected. And if it was on a network, you would see the QuestNav's IP address. So when you do that initial setup on your robot, you might have to look in here to see what is the IP address so that you can open up that configuration interface. But it shows connected to network tables. So now I'm going to open up Advantage Scope and connect it to the simulation. And hopefully the robot will move. There we go. It doesn't like it when I move off the field. So I have to move it forward from where it was in the direction that we have it on our robot. But now it's actually moving. This is showing our pose that we're merging together with odometry. If I want to see just the Quest pose, I have that here. And because of the way that I set it up mounted on my robot, it's in a kind of funny spot. But see, I can, as I tilt and move it around, it actually moves around. And the green one is where we're saying our robot is on the field. So, like depending on the game, this may or may not be useful. If you're climbing, it might be kind of neat to see that in the logs, but say you're on the charge station in 2023, which was like a big teeter-totter thing, you could see that, or you could even use that data to see what position you're in. So any questions to this point? Yeah, question.
So you guys have an elevator on your robot, right?
Yep.
So anytime you raise that elevator, the robot levitates.
So the question was, we had an elevator on the robot. The Quest was mounted on the elevator. Did the robot think it was coming off the ground? It actually didn't move with the elevator. It was on the fixed part. And last year, QuestNav didn't tell you all 3D. It just gave you 2D pose. Now it gives you 3D. But yeah, it didn't move up and down. It was on a fixed spot on the robot. Yeah, question? The question is tracking an issue? Like if you're moving really fast, it works really well. Like it's as long as it kind of works like it's on a human head, it works really well. So like if you mount it upside down, the cameras may not be able to see the ground. That might not work. We did have a problem at practice that we never really got to the bottom of. We started on one side of the field, like on the blue side, and everything was working great. And then we walked it around the red side without walking it around the blue side, and then ran it on the blue side, and it got lost. And our theory was like maybe it mapped the red side and then thought we were over there, and like all of a sudden realized it wasn't. So like you want to bring it around the field probably during calibration and let it map the field out, and then they say to just leave it on the whole time. So if you can power it by your robot, that's the best way to do it. Then it knows that you move to the pit, it maps all of that area too, knows as you move around, instead of like covering it up or turning it off so that it has to take some time to figure out where it is. Other questions? Yeah.
You said this doesn't read April tags yet, but could you give it like what the, like, not the game is, but like where you have to store it, what it looks like, so it can auto aim off of it?
Yeah, the question was, can you, so it doesn't read April tags to know where you are, but can you do like object detection to be able to see game pieces? QuestNav doesn't have object detection built in. The Meta Quest does have some APIs for that. Somebody could definitely write an app to do that. Yeah, but to see game pieces or field elements and detect them, it doesn't have that built in, no. Yeah, question? Yeah, the question is, does it, if it maps between like the pit and the field, does it save that like the normal Quest does? All of that is just built into the Quest. QuestNav is just taking advantage of that. QuestNav doesn't actually do any of the mapping or any of the localization. It actually is built on Unity on top of the Quest Nav, and it just asks Unity, where is the camera right now? And then sends that data over network tables. Yeah.
How excited do you think teams should be to try and implement this? Like, is this we are 100% doing this thing? Or?
The question is, how excited should teams be about using this? I think it's really great. When it was working, it was like millimeter precision. Like we ran auto and it drove up to where it was supposed to be, and it like slowed down and just was right exactly where it was supposed to be. But when it didn't, it just like suddenly thought it was somewhere else, and it ran into the wall a couple times. So I think that was a problem with getting the mapping right, taking it around the field and getting a best practice for what are you gonna do at the start of an event. They have talked about trying to put some of that together on the documentation. There's nothing there yet. But certainly, you know, look at what's on Chief Delphi, talk to other people about their experiences too. But last year, our team didn't find out about it until January. We just like didn't see it on Chief Delphi. And then it was like, well, we're already in the season. This seems like an off-season thing to try to get going. And we thought, well, let's put it on our robot, see if it works. Maybe we'll use it. And it worked really well, but then like it didn't, and we didn't have time to figure out why. So, but there's been a lot of improvements on it too. I'll cover that a little bit, but we had like some network table disconnecting. They now use the WPI Lib network table library, so it's more robust. That web interface, you know, some of the things that there's been a lot of improvements to it since last year too. Yeah, question. Sure, yeah, the question is, can it or should it be used with April tags? And unless they add April tag capability to it, I think, yes, that probably, yeah, because the April tags can tell you where are you on the field, and then this can tell you where have you moved since you knew where you were last. So yeah, April tags would be helpful at the beginning, but you could also, we'll get into the code in a second here, but you can like fuse those data together. And so like if one or the other gets off, you can start pulling back into the position that you're supposed to be. Yeah, you can definitely use them together, yeah. And there's stuff built into WPI Lib to be able to do that. Yeah. All right, so what does the robot code look like? It's actually pretty simple. There's not a lot that you have to do in your robot. Kind of depends what you want to do with the data, but to just get it basic working, it's really simple. So you need to tell the code where is the quest on your robot, just because like you probably want to know where the center of your robot is on the floor. The quest nav is, you know, up on your robot, off center. So like when the quest spins, it's going to make like a circle around the center of your robot. You want to know that your robot is spinning perfectly. So you just have to know where is it. Really X, Y, and yaw are the most important unless you're going to use rotation and pitch and roll. So you need to know how far forward or backward from the center of the robot is it, how far left and right is it from the center, and how high is it, and then what's its rotation. I would recommend mounting it like it's on someone's head in this sort of an orientation, not sideways or upside down, because it has downward pointing cameras that probably see the floor. If they're flipped up, you know, in a lot of our venues, it's going to be looking really far to the ceiling. So once you get that, you save that, and you'll need that later. And then that vendor library gives you this class called QuestNav, and you can use that to interact with the QuestNav. You need to call command periodic somewhere every period. A lot of teams are going to just put it in their drivetrain subsystem. That's probably where I would put it. And then subsystem has a periodic method that gets called. So you just put QuestNav in there. You put command periodic in there. So that does your basic connection. And then this is how you would actually get the data and fuse it together with your odometry to track where you've been moving. So there's this get all unread pose frames on the QuestNav object, and that'll give you all of the frames since the last time you called it. So the quest runs at 120 hertz, which is 120 readings per second. Your robot loop runs at 50 hertz. So you get 50 loops per second. So every time you're gonna have multiple, 2 or 3, sometimes 4 if you got a little behind, pose frames that you can read. This will read them all. And then you can just loop over them. There's an is tracking property on that frame, just to know, did the Quest think it was tracking at that time? Like if the cameras are covered up or there's something not working, you don't want to use that data. So you just want to check, was it tracking? And then you ask, what was the 3D pose of the Quest? So it knows where it moved on the field, not necessarily where your robot moved. And then here's where we use that robot to Quest transformation. We can just take that pose, transform it by the robot to Quest in reverse, and that will map us to the robot position. So now we have where we think the robot is based on the Quest data. And then we can call add vision measurement on the CTRE swerve library has this built in. You just call that method, and so does YAGSL. So that's what most teams are using one of those two for their swerve. If you're not, you could also just be using one of the built-in pose estimators that are built into WPI Lib. That's what like YAGSL does underneath. So you add that vision measurement. You could even just use it directly if you don't want to fuse it with anything else. You don't want to fuse it with April tag data. You don't want to fuse it with odometry. You just trust it, that it's where you're supposed to be. You could just use it directly or transform it by your starting pose and just use it straight up. So if you're going to use a pose estimator, what a pose estimator does is it takes your odometry data that we talked about, like based on your encoders and your IMU as you're moving around, and it compensates for latency automatically. So a lot of, like your vision measurements are going to take some time to come over the network. So it knows, like, I took this picture and sent this data 4 milliseconds ago. It'll go back 4 milliseconds, apply that where you were, and then put your wheel odometry on top of that to figure out where you are now. And you can set standard deviations on the pose estimator. So like, do I trust my wheel odometry more, or do I trust my Quest data more? You're probably going to have a very small standard deviation on your Quest and a very large standard deviation on your odometry. And if you want to use April tags constantly while your robot is driving, you would also feed that data in, and you would find a good standard deviation to use for those. And so you feed all of that data into the pose estimator, and it does filtering and gives you back a pose estimate. Yeah.
Can you zero that even during a match? Like when you press a button, was it looking at a April tag or the Quest, where it's looking at something and you can zero it back out so that it would know where you're at?
Sure. Yeah, the question is, can you zero it? I guess that's the other part that I didn't include in the demo, is like at the beginning of the match, you're probably going to want to reset your pose, or even throughout the match. So I put it in my drivetrain subsystem. If I can find it. There we go. Thank you. Okay, so here I had commented this out because this isn't in the beta, the released beta that thing installs yet. So here I'm doing that. I'm also sending that data over the network table. That's how I had that one that was floating on the field, was I didn't feed it into my pose estimator. I just straight up did it. But in here, I have a reset pose. So if I know where I am on the field, I can call reset pose on my command swerve drive, and it will reset the pose on the Quest nav. And that actually sends it over to the Quest, and then it will automatically apply that. From now on, it'll know, where it is on the field. And then I also reset the pose on my pose estimator, because it needs to know that I've moved to.
Does that have any effect on your mapping of the space?
The question is, does it have any effect on the mapping of the space? It doesn't, no, because this just gives it like an offset it starts at 0, 0, and you tell it it's at 1, 1. Now it's constantly just gonna apply that offset on the quest. Yep, so it doesn't change the mapping, it just changes the way that it processes that estimate. All right, so yeah, if anybody looked at it last year, we looked at it last year, decided not to use it yet, but there were some new features that improve networking. It uses the native WPI lib, so it's a little bit more robust. Nothing against the way it was implemented before, but this is now the official code for network tables. It uses that. It has that web installer that we just went through. That makes it way easier to set it up. It was a whole process to go look at all these little settings that you had to get right. That configuration dashboard, after we got it installed, that we could see what was going on and set our team number, that was really nice here, but I think that's gonna be super great when it's on your robot, because once it's mounted on your robot, you can't look through the eyes unless you take it off. So it's really nice to be able to do that. That's part of too, using like something like this to be able to see what's happening on it. Even when it's on your robot, you can run this so that you can see what it sees. The 3D tracking, it now knows its height and pitch and roll. That was added. The auto start, there were some hacks like that you could install an app that you had to side load that you could tell it to launch on start. Now it's just built in. So you install it, restart the quest nav will launch automatically. And it has some improvements to keep tracking alive. Some of that stuff that we saw, like to not go to sleep, make sure that the tracking keeps working, and then some efficiency for better battery life too. Even though it's still running at 120 hertz, there's some additional improvements for battery. So I hinted at maybe coming soon is April tag integration. That would be cool if they get that going. There's also an open pull request right now for pass-through video streaming. So maybe you could see something like this, or even just the pass-through data. Maybe you don't see the quest nav, and you could put that on your dashboard, like on your Elastic, on your driver dashboard. So that is almost certainly coming. The April tag integration, I'm not sure. That may or may not make it. So yeah, any other questions? This barcode will take you to the website where these slides are, and then we'll hopefully get a link up to the YouTube too if you want to watch it again or share it with your friends. But any other questions? Yeah.
My question is about like long-term support. It's like, do you think that this is a team that plans on maintaining this into the future, or is this kind of like a one-off side project that somebody's working on and maybe it'll go somewhere?
Sure. Yeah, the question is about long-term support, right? That's always a question with open source stuff. Like, is this something that somebody's excited about now and they're working on and then they're gonna forget about it? Time will tell. That it's open source, which is my favorite thing, like compared to some of our other things that we buy. We don't know what's happening. So like the 3D tracking and the auto launching, those are pull requests that I actually created and sent to them, and they integrated it. So they can integrate it, or I can pull it down and continue to maintain it myself. It's a pretty small set of contributors, I think 5-ish right now, but maybe if it takes off a little bit more, maybe there'll be more. But it's kind of a mix of mentors and students, it looks like, from what I can tell too. So like students are gonna graduate out, mentors maybe would keep it going. So hopefully it'll be longer term. Yeah. Yeah, question.
So can you get the Quest Nav app on older models like the Quest 2, or do you need a 3 to 3S?
The question is, can you run it on older Quests like the Quest 2? I've seen some people say that you should be able to, but I haven't necessarily seen anybody say yes or no, it did or did not work. Yeah, I'm not sure. Any other questions? All right, well, thanks, that's it.
overshoot the target, and then it's gonna try to power back towards the target, and then it'll just keep going that way until either you turn the robot off or so. What can we do to solve the issues of a peak? If you have a set point, it's just gonna prevent you from overshooting so that you get to the exact spot that you need to be without having any oscillations. So returning to the two scenarios before, so on a country road, it doesn't really apply, but because you're trying to maintain a velocity, if you have like latency in the system, it might be useful, but any sort of mechanism like that, your P gain will do just fine. But in terms of parking, as you approach the spot, you're obviously going to hit the brake a little bit to slow down, so that way you get to where you need to be and don't overshoot your parking spot. Now, as for a PD controller, these allow you to use a much more aggressive P value, so that way you can get to your spot faster, and it'll also improve precision. So if there's anything external, it'll counteract that much easier using that much more aggressive P gain. So some cons to a PD controller. It still does not account for any predictable variables. So like any gravity, any friction in your mechanism, you're not going to be able to account for that, and that may result in some errors down the line. Now, tuning a PD controller, what you can do with it is you start by upping the P value until the mechanism starts to oscillate around the set point. And then after that, you up the D value until it stops oscillating. But you gotta be careful as well, because too much derivative value and your mechanism will oscillate and it'll be slow to reach the set point. And then you can just repeat this process until you get the desired result. So PD controllers are good, but what can make them better? So we still have these variables that are unaccounted for. We've got gravity and friction, and we can counteract those with feed-forwards. So when you're driving a car, the feed-forwards are kind of like your brain. You know how your car behaves, and you will push the gas accordingly. So in terms of feed-forwards, as for the motor controllers they can run on, CTRE can run these on almost all of their controllers. But Rev is limited. They do actually have max motion now, which can run some of these, but CTRE is a lot more advanced. You can also run PID controllers through WPI Lib on your Rio, but in some cases that can take up some computing resources, and it might be better to offload it to a motor controller if possible. So why do we use feed-forwards instead of an eye controller? Any guesses? So the main thing with eye controllers is that they're reactive. So any sort of predictable variables it's going to account for after the fact. And if you have like an arm where like if you're sitting here and counteracting gravity with your eye controller, when you go to the other side, it's going to sag a little bit until that eye controller catches up, when we would prefer that it just gets to the right spot right away. So feedforwards are proactive. You measure them beforehand, and your motor controllers can act on them without any delay in response time or loss of precision. So what types of variables do we account for? So as I said before, there's static friction and there's also gravity, but there are a few others. And we'll go through a couple of them pretty soon. So first off, this is the biggest one, is your gravity. This one is the most important feed forward that you will use. And yeah, there are two different types of gravity that you can account for. So there's a static mode where it's like, for elevators, anything linear, it's just a value that doesn't change and it just fights the gravity. That's all that it does. But then for mechanisms like arms, you use what is called a rotational cosine feed forward. And what that allows you to do is essentially just account for gravity no matter where your arm is positioned around a circle. So, yeah. So this, driving a car up a hill, is a lot like an elevator. It's a static feed forward. So when you're driving uphill, you're going to need to apply more gas so that you maintain your speed. That's pretty much all there is to it. So, yeah. And then for the rotational cosine, if any of you have taken pre-calculus, you'll know what this is. This is called a unit circle. And in those parentheses, each of the numbers on the left, that's your cosine function. So as you can see on this side here, so when the arm's over here, it's applying a -1 to your gravity value, so that's essentially counteracting it this way. And then as it goes up, it just moves closer and closer to 0 because you have to fight gravity a lot less. And then on the other side, it's positive, so that way you're fighting in the other direction. And then as you move up, it's closer and closer to 0, and same goes for the bottom half. So as for tuning your gravity constant, all it really is if your mechanism is falling downwards, you just up it a little bit. If your mechanism is moving upwards, you'll have to lower it. A well-tuned kg for your mechanism will make it stay in place no matter where it's at. And that'll let your PID controller take over from there, and it'll be a lot more accurate. The next type of feed forward is for static friction. This one is called KS, and it's just how much power you need to overcome static friction. It's really useful for pretty much any type of mechanism, especially swerve modules, because swerve modules have a lot of static friction because the wheel is touching the carpet, and there's a lot of resistance there. So, real quick, what is this component of a car? So, this is a clutch. And what it does is it essentially decides when you're going to apply power to your car. Now, KS is kind of like engaging the clutch on a car, so it's how much you rev your motor before you actually take off. If you have too little, your engine is going to stall, so your mechanism won't be able to fight the static friction and it will not move. But if you have too much KS, it's going to be like doing a burnout in a car. You're spinning your wheels really fast, but you're not getting anywhere. And on a robot, that looks like some more oscillations. And it might cause it to oscillate uncontrollably. Now, when tuning KS, the process can differ just a little bit with an arm or an elevator. So with an arm, you're going to want to put the arm in the upper position, and that way you can just slightly raise the value until it falls over. And that's really all you need to do for that. It's the value it starts moving at. Then with the mechanism, a light tap, just a light tap should be able to get it to move. Then with an elevator, you're going to want to tune kg before moving to KS on an elevator is what I would recommend. So that way you can have your elevator in a like a halfway raised position, and you can see when your elevator moves up and when your elevator moves down. So you can up the KS very slowly until it starts moving. Then if it moves one way but not the other, so you're going to set your set point either above or below where you're at. If it moves one way but not the other, you're going to have to adjust the kg very slightly in order to counteract that. But again, a light tap should be able to make it move in either direction. And then some other values. KV is just how much power you need to maintain a certain unit of velocity. So that's just going to be like how much gas you give a car to go 55 miles an hour. So Ka is how much power you need per unit of acceleration. A lot of times you don't really need these for a PID controller with FeedForwards, but sometimes they could be useful, but I haven't really found a need for them just yet. So when you put PID and FeedForwards together, you're going to want to set all your gains to 0 and start with your FeedForwards. So tuning gravity, tuning static friction, anything like that. Then once that's done, you just tune the PID like you did before, up the p-value, then counteract it with the derivative term. So some resources and links. WPI Lib has some tuning simulations, which are pretty good. The simulation does have some latency, and the KG feed forward does not have the arm cosine value, so that could be a little bit problematic, but that's all there is to that. Then I do recommend looking at the CTRE Motion Magic docs as well if you want to look at CTRE's motion profiler and how to use the PIDs with that. So, do we want to look at some examples in code? Is that something we want to do? All right. Let me get that open. All right. Let me go. All right. So if I could move this over. So here we have our tuner constants file for our swerve drive. It's auto-generated from CTRE, so they have a tool for that. But we did tune these PID controllers. So KS, 0.3 volts is what it took to make those swerve modules turn on the carpet. And then from there, we did KP and KD. And then for the drive gains, we used a tool called SysID, which stands for System Identification. And what that does is it's a tool that will do a certain routine where it'll slowly ramp up the power you're applying to the motors. And then by using the data, you can see these. It'll suggest some values to use for these. So, yeah, that's what we did for that. And then for the elevator, let's see if I can find it. We used the Motion Magic from CTRE, and we actually have 3 different sets of gains. So just looking at these, why do you think we would want 3 different sets of gains for the elevator? So we have 1 set of gains for going up. Yeah, right here. These are the gains for going up. So when the elevator is traveling upwards, we actually have a slightly different set of PID gains. I believe the KS is slightly, nope, the KS is the same. Our KP is slightly lower when going down because essentially the reasoning for that is that if it were a little bit higher, the elevator would slam into the bottom of its travel distance. So we just wanted to avoid that so that we don't break stuff. And then we also have a separate set for climbing. And this one, so we actually used our elevator as a climber. So we would raise the elevator, grab onto the cage, and then pull the elevator down in order to climb. So the biggest difference with this one is the kg, because you'll see that this one is actually a negative value because we're trying to pull the elevator down, essentially fighting the weight of the robot, which is the main force that actually gets us up off the ground. Then we also have a slightly higher KP to go with that as well, just to get it up there as well. Does anybody have any questions?
So when you're tuning these values, like what recommended increments would you go by? Because I'm sure like changing it by like hertz or like it's going to be a lot different.
It depends. Depends on how much power you need to move your mechanism. A lot of times, I'd say it's something you get a feel for after a while, but I'd say the best advice is to go like probably 30% of what you have as the value. Just increase it by 30% and just somewhere around there. It's nothing super exact. It's just, you're just gonna get a feel for it after a while. Any other questions? I guess that's all I got then. Yeah, so if you have any questions, you can just email our team email and look and ask for my assistance. So, yeah. All right. All right, we're gonna get started here pretty quick. All right, so today, this presentation is about commands and command sequences. I am Evan Kempen. I am the lead programmer on FRC 4607 CIS. Today, we are talking about commands. So, what are commands? They're essentially just a tool in your code that lets you sequence actions and make decisions. So, commands are made of 4 basic parts. The initialize, execute, is finished, and end methods. So, starting off with the initialize method, this is anything you want to happen when your command starts. So when it's first triggered, like you can, like if you're going to intake a game piece, you can set a has game piece boolean to false as the command starts. Then for the execute command, this is anything you want to happen while the command is running. So this runs once every loop period, so every time the robot goes through its code, if the command is scheduled, it will run this method. So anything that needs like controller input is going to use this, like triggers and joysticks especially. Then if you want to measure anything and make decisions like using a PID controller inside of a command, you can do that as well. Then the is finished method, probably the most important method of a command. It is what determines when your command ends. So this essentially runs once every loop period, and if the condition is true, if this method returns true, the command will end. So like if your intake velocity is below a certain threshold, which indicates that you have a game piece, it's going to end the command there, and you're done intaking the game piece. Then the end method. This just runs once the command ends. So like once your intake game piece command is finished, you can set that has game piece boolean to true in order to tell the rest of the robot that it has a game piece. It also has a boolean called interrupted. So you can pass a value, well, it has a boolean called interrupted, so it just determines whether or not, well, I wouldn't say determines, but it's essentially if your command finished naturally through the is finished method, or if it got interrupted by some other command. All right, so the command scheduler, this is the brains of the entire operation. It keeps track of any commands that are running, what subsystems they use, as well as any command groups that might be running as well. So continuing on with the command scheduler, essentially, if two commands have the same subsystem in their add requirements method, it'll just cancel the old one, and the more recent command will run. So this prevents your robot from running two commands at the same time, which require the same subsystem, which could cause problems. And then the command scheduler also lets you get which commands are running. So if you wanted to see whether you're currently aligning to a scoring position or in taking a game piece, you can see that. You can also schedule commands directly, which I guess has its uses occasionally. And then you can also assign default commands. So any command you want to run, there's no other command scheduled. Like on each robot, this is probably going to be driving for your drivetrain. When nothing else is scheduled, you're going to want to obviously be able to drive the robot. So, yeah. Then moving on to command sequences, there's a few different types of groups. Sequential command groups, parallel command groups, which have three other types, which are normal, race, and deadline, as well as conditional commands. So, real quick, show of hands, who here has been in FLL or FTC? Got one over there. So, essentially, with these command sequences, it's very similar to block coding if you've ever done that. It's super simple. It's like working with a flow chart. So, yeah. Sequential command groups, these are essentially just, they run commands in a sequence. So, whenever one command ends, the next one starts, and so on until the end of the command group. And then this one ends once all the commands are finished. In a flow chart, it will look like this. So, moving from top to bottom, it'll start with command 1, then once that finishes, it'll go to command 2, and then command 3. Next up is parallel command groups. These are useful when you want to run commands simultaneously. It just lets you save some time. So if you needed to go to like a scoring position, you could run your arm and elevator at the same time. And then the three types of parallel command groups. There's a regular command group, which just runs all the commands and ends once all of them finish. The parallel race group ends when any of the commands in the group finish. So the first one to finish in that command group will then cause the rest of the commands to get canceled, and it'll be done from there. And then there is also a deadline group, which is very similar to a race group, but instead of any command, you pick one specific command to be the one which determines when it ends. In a flow chart, it's going to be a box with all the commands in there side by side. So yeah. And on to conditional commands. These are very useful. They let you use logic in your command sequences. It's pretty much an if-then-else statement, but formatted as a command. And it can be really helpful if you have problematic mechanisms. And by problematic, I mean they like to collide with each other if they're in certain spots. In a flow chart, they're going to look like this. Condition up top yes or no. If yes, it'll do the command on the left. If no, it'll do the command on the right. So, now we're going to move on to a couple scenarios. So, for these, you're going to want to be mindful of where all the mechanisms are at. And we're going to see what a few command sequences look like. So, this is our robot. It has an elevator that goes up and down and an arm that can rotate 360 degrees. So, the important thing for that arm is that it will always take the shortest path to its destination, which can be problematic because it might collide with the bottom part of the robot if you're not careful. As for the commands that we're going to be able to use in these scenarios, we're going to be able to use a move elevator command, which just moves it to a certain position. Same with a move arm command, and then we can also use all of the command groups as well. So, our first scenario is placing coral. So, our goal is to go from an extended position, setting a coral on the reef, to a stowed position, as you can see in the images over there. And for this, there are two possible solutions. We can use either a sequential command group or a parallel command group. Which one should we use?
Parallel.
Parallel?
Yep.
Why is that? What?
Well, with the way you've set up the sequential group, the elevator we can move first, then you have to back the robot up from the coral reef, from the reef before you can actually do that. Parallel,
Yes.
they both work at the same time, meaning that the arm won't get caught on the reef. At least
Yes,
that's
that
the
is fair. Would it be a possibility if we were to reverse the commands in the sequential command group? What if we did that?
Well, then you take the
you
coral
Yes.
off.
Then you do this. Actually,
You take the coral off if you moved it back up without releasing the coral.
I think you need to. If you did reverse it with the move arm above the move elevator, the sequential, I think that could work too.
Yeah.
They both
So-
could work. It's just in the example you have right here is the parallel you want to go with because the sequential will
Yeah.
go with reef first.
So, if you picked a parallel, the video is not showing up. Oh well. Anyways. Oh, there it is. So, let's see. Can I play that? So, in the beginning of the season, I'm just gonna let this play. Yep. So, like you said, the parallel command group did still have some issues with the arm colliding with the reef. So, if we go back here, again, the parallel moves them both at the same time. So what I did to fix that is I used a sequential group, which actually moved the arm first. So this will be replaced with a move arm, and this will be replaced with the elevator. Question?
I was gonna say earlier, the only thing that I could see happening is if your elevator is too fast, then your arm can't get out of the way in time, and then stuff happens.
Yes, that's the entire issue, is that the elevator was too fast and the arm did not move out of the way in time.
But if,
So,
if you are able to, you could put a sequential group in the parallel group. So you move the arm, and then after like a short delay, move the elevator while the arm is like still moving a little bit. You want maximum efficiency.
yeah, so actually one of the things we can do is we get to choose when the move arm command is finished. So what we actually do is we set a tolerance in degrees. So we want the arm to go to a vertical position, right? But you can tell it that the command's finished once the arm is like over here. And then since we set a set point, the subsystem will continue through it, but it'll finish the arm command, which will then give the elevator the go-ahead to go back down. So that's what we did for that. All right, so for our next scenario, we're gonna do an algae intake. So the goals for this one are to make the arm and elevator go from any possible position that they could be in to one suitable for intaking algae on the ground. So essentially, arm is off to the side and the elevator is all the way down. So I'll start us off with this potential solution. So what we can do is we can move the elevator to a pass-through height right away, just to make sure that that arm doesn't collide with the robot. And then from there, we can move the arm to its position, and then move the elevator all the way down. So, yeah, does anybody have any ideas on what we could do to improve this command? Yes.
The only thing is what you could potentially do is, now of course you might still, this is spare me for a second, is you could do a parallel command with the arm moving, and then have a sequential with the move elevators. So the arm can move to the thing, collect the thing, and then with the elevators, it would start moving back up. But that's only if you want speed, pure speed, not just hitting yourself. And I bet you could make it if you decide to do two separate commands, one for if it's low enough where it could hit itself, and one for when it's just anywhere else.
Yep.
And that probably would make it a little more complicated, but it could make it faster from any other position.
Yes, that's actually the exact solution, that second solution. We can employ the use of a conditional command. So essentially with this, we can tell if the arm will take the upper route if it's within like a certain area of where it needs to be. Then if it will take the upper route, we're just going to do an instant command. So what that is, it's just a command that does nothing and finishes instantly. That's all that it does. But if the arm will not take the upper route, it's going to move the elevator to a pass-through height, and then continue like normal. There is still one other thing we can do to make this slightly faster. So, any other ideas there? Yeah?
If the arm does take the upper route, then the two commands in this sequential command could be parallel.
Yeah. So what we're going to do here is we're going to nest command groups within this conditional command. So if the arm is going to take the upper route, we don't care where the elevator is at or where the arm is at. We can just get to that position as fast as possible because we know the robot will not collide with itself. But if it's going to take the lower route, we're going to return to the original sequential, which will raise the elevator to a pass-through height, then move the arm, then move the elevator to its final height down below. So this video, it's a fun one, and it's just a reminder of how your robot will follow your instructions to a T.
Step 1, get 2 pieces of bread out. Got 'em.
This dad's teaching this kid a very valuable lesson, but the way that he does it is hilarious. Take a look at this funny video.
No, Dad, with the peanut butter.
I'm just doing what it says. It says take 1 piece of bread, spread it around with the butter knife.
Hold on.
Get some jelly, rub it on the other half of the bread.
No, Dad, open the jelly.
Well, it doesn't say to do that. Put the breads together on top of each other. Take a big bite.
Sorry, I had to make it extremely specific.
Oh, good. I'm starving. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop a bit of peanut butter out of
That means like a lot.
A bit means a lot?
In my world.
There we go.
Doing better than before, though.
Open the jelly jar. Squeeze it onto the other piece of bread.
No.
Done. Close it. Brad, get some peanut butter. Take the peanut butter knife. Open the peanut butter. Put the knife in the PD. Get some jelly. Open the jelly. Squirt the jelly onto the bread. Take the butter knife with the peanut butter on it. Wipe it all over the piece of bread that's blank. Take the butter knife, rub the jelly all over the piece of bread.
Oh, you're doing better.
It's all over. Put the 2 pieces on top of each other.
This is how I meant.
Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop some of the peanut butter out of the inside of the jar. Spread your scoop of peanut butter onto one of your pieces of bread with the knife.
No.
Squeeze some jelly onto the other piece of bread. Spread the jelly on the bread with the butter knife. Put your 2 pieces of bread, peanut butter and jelly sides together. Done. Get some peanut butter. Get some jelly in the peanut butter. Get a butter knife. Put the butter knife in the peanut butter. Take the butter knife out of the peanut butter.
You did it wrong. No.
Take 1 piece of bread and take the butter knife that has the peanut butter on it, spread it all over the top of the piece of bread. That's the top.
I mean the sides.
Squirt some on another piece of bread. Take the butter knife, rub it all over the top of the piece of bread.
I quit. It wasn't making any sense. Sorry, you ruined it on purpose. He knows how to make one.
He's a purpose. You want to take your sandwich with you? Glad I made that for you.
I edited a bit.
Take 2 pieces of white bread, take the lid off the jar of peanut butter. Get a butter knife and stick it inside the peanut butter jar. With the knife, scoop some of the peanut butter out of the inside of the jar. Spread your scoop of peanut butter onto the face of one of your pieces of bread with the knife. Squeeze some jelly onto the other piece of bread. Spread the jelly on the bread with the butter knife. Put your 2 pieces of bread, peanut butter and jelly sides together. Done.
Now eat it.
Not the best,
Oh, you made it.
but I think it qualifies. That's a win.
All right. So, anyways, what did we learn from that video?
How to make a peanut butter and jelly sandwich.
In the most
Yes.
earth ways possible.
You guys?
Make it extra specific.
Yes.
Variables that can go wrong.
Yes, exactly. There are a lot of variables that can go wrong. So you always want to keep a keen eye for anything odd that's going on with your robot. Like, even if it doesn't, like, seem to affect anything, it might later. So when an issue shows up, always document it so you know what you're trying to fix, find the root cause. So diagnose the problem, and then fix and test it to make sure that it's functioning correctly. So some unintended behaviors can be dangerous. So, like, imagine, like, if that butter knife was an actual knife, the guy could have gotten seriously injured by that with the wrong side of the knife in there. So one example of this that happened to us last year is there was a certain command for processing algae, so the elevator would have to go down, but I did not have the foresight to make sure that the elevator would clear the bottom of the robot. So essentially all that it did is it, like, when it was going to the processor position, it moved the arm and the elevator at the same time and slammed into the belly pan. So that was something that did not need to happen, but it was just something that slipped. So always watch for those odd behaviors. So yeah, that's all I've got for slides. We can go through some code examples if we want. Is that something we want to do?
Show us some spaghetti code.
All right.
No, but it's funny.
So
Especially when everything breaks.
this is our robot code from last year. And this is our robot container where we essentially just bind all the commands to buttons. So if I could find my mouse, there it is. Essentially, this joystick dot B on true, this is what's called a trigger. So whenever that happens, it's going to do what's in the parentheses. So it's going to do what we call a lollipop stow, which arm vertical, elevator down. And then it's also going to essentially just make sure that the servo is retracted, because we have a little servo that locks the elevator in place when climbing. So anytime we move the elevator, we just want to make sure that servo is out of the way. So yeah, that's that. There are also some inline ways to do command sequences. So like this along with here, that's essentially denoting a parallel command group. Then there is also this and then, which is essentially denoting a sequential command group. So as for an actual command, I think, yes, it's this one. So this is a command for essentially intaking coral. So what this one does is it, in the initialize, it sets the LEDs to let the driver know that it's prepared to intake coral. So then with our manipulator, we set the coral state to false. we set this is at velocity to false. Then what we do is we then just set a fixed amperage to the manipulator motor to essentially just run the motor at a certain amperage. Then while this is running, what it's going to do is it's going to check to see if the manipulator is at its velocity, if it's at its target velocity. And it's going to set the is at velocity variable to true if it is. Then the is finished method, what it's going to do is it's going to return true if the manipulator both is at velocity, so if the manipulator got to 60 RPMs or whatever, then it's going to see if the manipulator's actual speed is now less than 50. So it's going to get up to speed, and then once the coral enters, it's going to hit a stopper at the back, which will then stop the manipulator wheels, which will then make both of these true, and this is finished will end the command. And then as for the end method, it's going to set the LEDs to say that the robot has coral. And then it's going to set it to a holding amperage, like a holding duty cycle, to make sure that it doesn't fall out. And then it's also going to set the has coral value to true. Any questions so far? All right, let's move on to a command group. So this one is a sequential command group. So when we create this command, it's going to use what we call a super. So it's going to essentially nest it all within a sequential command group. This super just means it's going to take the type of command that this is. So it is a sequential command. And then inside, we are going to have a parallel command group, which will move the windmill to a, what is that? Can't quite see from here, but it's going to move the windmill to a position. I believe, oh yeah, it's going to move it to a horizontal position, which will prepare it to intake coral. Then it's going to do a conditional command. Now, with a conditional command, the condition is denoted at the back of the command. So we have on true, on false, then the condition. So what we're doing with the condition here is we're essentially just trying to see if it's on a certain half of the possible position. So like we did in the algae scenario, it's going to see if it's going to take the top route or the bottom route to its set point. And if it's going to take the problematic route, it is going to essentially just move it to a position that is suitable for, like, if it is going to collide, it's just going to move the windmill out of the way so that it doesn't. Oh, I guess this parallel command group does not include this windmill one, so it includes this elevator one. So this is all a group. So it's going to move the elevator up and also check to see if the windmill's going to be problematic. Then once it makes sure everything is clear, it's going to move the windmill to the position that it needs to be. All right. Any questions? All right, is there anything else anyone wants to see? All right. I guess that's all for this presentation.